Out in the cold silence of the cosmos, where galaxies drift like whispers in an ancient void, there lies a cosmic event so powerful, so raw, and so revealing that it has shaken the foundations of what we believe about the very fabric of reality. This is not fiction. This is not an imaginative leap of theoretical speculation. This is the Bullet Cluster, the grand celestial collision that has gifted humanity with a rare glimpse behind the cosmic curtain. It's a scene of two galaxy clusters smashing into one another with incomprehensible force, revealing invisible clues about the hidden scaffolding of the universe itself. What lies beyond what we can see? What truly makes up most of the universe's mass? The Bullet Cluster may just be the strongest evidence yet that something invisible, and profoundly mysterious, surrounds us all. But before we continue, subscribe to the channel so you don't miss out on any of these videos. We begin by looking into the infinite distance, a stretch of the cosmos roughly 3.8 billion light-years from Earth, where an event so massive and so old still sends us information in the form of ancient photons. Here, two galaxy clusters, massive groupings of galaxies, gas, and dark matter, have collided in a process that began hundreds of millions of years ago. The aftermath of their violent interaction remains frozen in time, not because the event is still occurring, but because the speed of light acts as a cosmic historian, delivering us images from an ancient past. The collision forms what astronomers now refer to as the Bullet Cluster, designated 1EO657-56. The name itself evokes motion and speed, and rightly so. The smaller of the two clusters tore through the larger one like a bullet, sending shockwaves across the intergalactic medium. This is no ordinary observation. The Bullet Cluster is unique. It's not just a crash site in space. It is an astrophysical laboratory, a moment suspended in cosmic time where forces both visible and invisible reveal their fingerprints. It is the visual proof that the universe is not composed only of things we can see, touch, or detect through traditional means. Instead, the Bullet Cluster provides us with a map of the invisible, a direct, empirical, undeniable indication that the cosmos is shaped by something more than ordinary matter. This is why scientists call it the smoking gun of dark matter. To truly understand the Bullet Cluster, we must unpack everything, from how galaxy clusters work, to the nature of gravity, to the elusive and controversial concept of dark matter. We need to dive into astrophysics, explore the electromagnetic spectrum, understand gravitational lensing, and interrogate the very foundations of our cosmological models. This isn't just a story about one event in space. It's a journey into what the universe is made of, why it behaves the way it does, and how a seemingly invisible form of matter may actually shape the very structure of existence. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain thousands of galaxies, trillions of stars, vast amounts of hot gas, and, as modern theories suggest, even more dark matter. These clusters move through space, slowly pulled by the large-scale structure of the cosmos. Every so often, in the immense timescales of cosmic history, two clusters come close enough to gravitationally interact, and sometimes they crash. When such a collision occurs, it is a titanic event. The stars within the galaxies, due to the vast distances between them, mostly pass by without direct interaction. The galaxies themselves slide through one another like ghosts. But the gas, which makes up most of the ordinary, or baryonic, matter, behaves very differently. It is subject to friction and interaction. As the two clusters collide, their gas components do not pass through each other easily. Instead, they compress, heat up, and emit X-rays. It is this hot gas, shining in high-energy light, that we can detect with X-ray telescopes like NASA's Chandra X-ray Observatory. But here's the puzzle. When we look at the Bullet Cluster through X-ray eyes, we see that the gas, the ordinary matter, has been slowed down by the collision. However, when we map the gravitational field of the cluster using gravitational lensing, the bending of light from background galaxies due to massive foreground objects, we find something extraordinary. The bulk of the mass isn't where the gas is. It has moved ahead, aligned with the galaxies themselves. This tells us that most of the mass, the stuff exerting gravitational pull, is invisible. It hasn't interacted like the gas. It has passed straight through. This is the moment that changes everything. The bullet cluster shows us, in spatial separation, two forms of matter: the visible, baryonic gas slowed by the collision, and the invisible, non-interacting mass, presumed to be dark matter, that kept moving unimpeded. It's the first time we have seen dark matter, not directly, but through its effects on space-time. The bullet cluster has become the strongest piece of evidence that dark matter is not just a theoretical convenience, not just a mathematical artifact, but a real component of the universe. Let's pause and appreciate the scale of what we're dealing with. The bullet cluster spans millions of light-years across. The shockwave from the collision, which resembles a Mach cone in supersonic flight, travels at roughly 4,800 kilometers per second. That's nearly 11 million miles per hour. The collision occurred over hundreds of millions of years, and its effects still ripple through the cosmic medium. Observing such an event is like studying a slow-motion explosion frozen in time. Each detail reveals secrets of astrophysical dynamics, particle behavior, and the very composition of the cosmos. To interpret this, scientists use tools from gravitational lensing, which relies on Einstein's general theory of relativity. Gravity warps spacetime, and massive objects like galaxy clusters bend the light from more distant galaxies behind them. This bending creates distortions, stretching, magnifying, and sometimes even creating multiple images. By analyzing these distortions, astronomers can map the distribution of mass, including the invisible mass. This is how they determine that most of the mass in the bullet cluster is not located where the X-ray emitting gas is, but around the galaxies that have passed through. This mismatch is critical. If there were no dark matter, we would expect the mass to align with the gas. But it doesn't. This leads us to a profound conclusion. The bullet cluster provides empirical evidence that something exists which has mass, creates gravity, but does not interact electromagnetically. This is the definition of dark matter. While dark matter does not emit, absorb, or reflect light, it clearly bends light through gravity. In the bullet cluster, we see this bending in action. It's as if the universe gave us a cheat code, a rare moment where the invisible becomes visible through its gravitational effects. But as with all scientific claims, alternative theories have been proposed. One of the main challengers to the dark matter paradigm is modified Newtonian dynamics, which suggests that perhaps our understanding of gravity itself is flawed at cosmic scales. Mond posits that instead of invoking invisible matter, we should modify the laws of gravity to account for the observations. However, the bullet cluster poses a serious problem for Mond. If gravity were simply acting differently, the gravitational lensing should follow the baryonic matter, the gas. But it doesn't. The gravitational field is centered on the galaxies, not the gas. This spatial offset cannot easily be explained by modified gravity alone. It strongly supports the existence of a separate, invisible mass component, dark matter. Let us dig deeper into the composition of this dark matter. Though we cannot detect it directly, various candidates have been proposed. The most popular among them are WIMPs, weakly interacting massive particles, and axions. These hypothetical particles interact through gravity and possibly the weak nuclear force but not electromagnetism. Despite extensive searches in underground detectors, particle colliders, and even astrophysical observations, these particles have not yet been conclusively detected. But the bullet cluster remains a key clue, a cosmic fingerprint of their gravitational presence. The bullet cluster is also a window into the dynamics of high-speed galaxy cluster collisions. The hydrodynamics of the gas, the behavior of the galaxies, and the distribution of mass all provide a unique dataset to test simulations and theoretical models. Computational astrophysicists create detailed simulations of cluster collisions, attempting to reproduce the shockwaves, mass separation, and X-ray signatures seen in the bullet cluster. These simulations not only help verify the existence of dark matter, but also allow scientists to constrain its properties, such as how collisional it might be. If dark matter interacted with itself or ordinary matter, we would expect it to slow down, clump, or leave other signatures. The bullet cluster suggests that dark matter is largely collisionless, passing through like a ghost. As our telescopes and analytical techniques improve, more examples of such cosmic collisions are being found. Yet none are as clear or as striking as the bullet cluster. Its clean geometry, well-separated components, and high-speed dynamics make it a cosmic Rosetta Stone, a key to decoding the invisible architecture of the universe. The implications ripple across all of cosmology. Dark matter is believed to constitute roughly 27% of the total mass-energy content of the universe. Ordinary matter, the stuff we see, touch, and build with, makes up less than 5%. The rest is dark energy, another profound mystery. But it is dark matter that gives the universe its structure. It clumps and collapses under gravity, forming the cosmic web of filaments and voids. Galaxies form in its gravitational wells. Without it, the universe would look profoundly different, flatter, emptier, and less structured. And yet, we still don't know what dark matter actually is. This fundamental ignorance, our inability to identify what constitutes the vast majority of the universe's matter, is what makes the bullet cluster all the more important. It isn't just an astronomical curiosity, it's a cosmic confrontation with our own ignorance. The image of the bullet cluster is not just a snapshot of a violent galactic crash, it is a snapshot of reality itself refusing to fit inside the neat boundaries of human expectation. It defies simplicity. It dares us to look deeper. Consider the instruments and observations that made this discovery possible. The Chandra X-ray Observatory provided the stunning X-ray image of the hot gas. Ground-based optical telescopes, such as those at the Magellan and Keck observatories, delivered the images of the galaxies. The Hubble Space Telescope added crucial visual and gravitational lensing data. All these sources were meticulously layered to build the multi-wavelength composite of the bullet cluster. Each observational layer is a different voice in a celestial chorus. X-rays revealing the hot gas, visible light showing the stars and galaxies, and lensing maps exposing the invisible. The final image is not just a picture, it's a scientific argument constructed from light itself. The colors in the famous bullet cluster image are not arbitrary. The pink hues represent X-ray emission, showing the hot gas that forms most of the visible mass in the cluster. The blue overlays are gravitational lensing maps, which indicate the locations of most of the cluster's actual mass, dominated by dark matter. The visible galaxies appear in normal color, riding along like tiny islands in a vast cosmic sea. And then, as you look closer, a separation becomes visible, a spatial mismatch between the gas and the mass. It's subtle, but clear. The collision pushed the gas back. But the mass kept going. This is not only visually stunning, it is conceptually explosive. Let's pause to imagine this in motion. Hundreds of millions of years ago, two massive galaxy clusters, each containing hundreds of galaxies, trillions of stars, and vast clouds of plasma, began approaching each other under mutual gravitational attraction. Over time, their trajectories curved inward. The smaller cluster accelerated as it fell into the gravitational well of the larger one. The gas clouds met first, smashing into each other, heating up to tens of millions of degrees, and glowing in X-rays. The galaxies, being relatively small and widely spaced, passed through each other with little friction. And the dark matter? Like a silent tide, it flowed forward unimpeded, unaffected by the plasma's heat or the collision's violence. In this way, the bullet cluster acts as a cosmic particle detector, an event large enough to separate matter types based on how they interact. Just like in a particle accelerator, where different particles emerge along different paths based on their properties, the bullet cluster separates gas, galaxies, and dark matter into distinct regions. It's a natural experiment on a grand scale, executed not by human hands, but by the universe itself. The story of the bullet cluster doesn't end with this single snapshot. It has spurred a multitude of follow-up observations, theoretical analyses, and simulations. Researchers have used the event to test models of dark matter self-interaction. If dark matter particles interacted with one another, we might expect them to slow down or scatter during the collision. However, the bullet cluster places stringent limits on such interactions. The dark matter appears to be collisionless. It doesn't clump, doesn't heat up, doesn't emit radiation, and passes through the collision like it's not even there. This simple observation places dark matter in a unique category of physics, a kind of matter that participates in gravity and maybe the weak nuclear force, but not much else. This has led theorists to refine their models. Some now believe that dark matter could be composed of WIMPs, weakly interacting massive particles, relics from the early universe. Others propose axions, extremely light particles that might arise from symmetry breaking in quantum fields. There are even more exotic theories, including sterile neutrinos, dark photons, or entire dark sectors with their own hidden forces and particles. The bullet cluster doesn't solve the mystery, but it narrows the suspects. But why should you care? Why should anyone, looking up at the stars from a small blue planet orbiting an average star in a quiet spiral galaxy, care about something so distant, so abstract? Because the bullet cluster is more than just an astrophysical curiosity. It is a mirror, reflecting our ability to question, to observe, to deduce. It shows that we, fragile creatures of carbon and water, can look into the sky and discern invisible truths. We can detect the unseen. We can build maps of the intangible. We can create meaning from silence. The bullet cluster tells us that our minds are not limited by our senses, that reason, mathematics, and light can reveal the invisible machinery of the cosmos. The implications stretch far beyond astronomy. Dark matter is a crucial ingredient in models of the early universe. Without it, the tiny density fluctuations in the cosmic microwave background would not have had enough mass to clump into stars and galaxies. The universe would be a thin soup of hydrogen and helium. No galaxies, no stars, no planets, and certainly no life. Dark matter is the scaffolding around which the luminous universe has formed. The bullet cluster shows us that this scaffolding is real. It's not a guess. It's not a placeholder. It's there, dragging galaxies with it, curving light around it, shaping the very structure of reality. And yet dark matter continues to evade direct detection. Despite decades of searching with ever more sensitive detectors buried deep underground, bombarded with streams of particles, cooled to near absolute zero, and shielded from every known interference, we have yet to capture even a single dark matter particle in a laboratory. This is what makes astronomical observations so critical. The bullet cluster, in its silence, speaks louder than any particle accelerator. It shows us that dark matter behaves as predicted, at least gravitationally. This gives credence to the idea that we're on the right track, that the invisible mass we've inferred from galactic rotation curves and lensing maps is not a mathematical mistake, but a fundamental part of reality. Still, the bullet cluster is just one data point. Astrophysicists have been scouring the universe for other collisions, other cosmic laboratories. And they've found some. One such case is MAX J0025.4-1222, another merging galaxy cluster with similar features. Yet each case has its own complications, its own limitations. The bullet cluster remains the clearest and most dramatic example, a benchmark against which others are compared. Its simplicity is what makes it powerful. Two clusters, one small and fast, the other large and slow, colliding nearly face-on, with minimal projection effects. It's a perfect case study, a gift from the universe. Let's revisit the numbers. The collision speed of the smaller subcluster, often called the bullet, is estimated at over 4,800 kilometers per second. That's more than 15 times faster than a bullet fired from a rifle. The gas is heated to over 100 million Kelvin, more than 8 times the temperature at the core of the Sun. The separation between the gas and the dark matter is on the order of 100 to 200 kiloparsecs, hundreds of thousands of light years. These are not small effects. These are vast, energetic, and measurable features, the kind that demand explanation, and that stubbornly resist any theory that denies dark matter's existence. The bullet cluster also challenges another idea, that of cosmic isotropy. If dark matter self-interacted more than just gravitationally, we might see irregularities, turbulence, distortions, asymmetries in the lensing signal. But we don't. The mass flows cleanly, the gravitational field lines up with the galaxies, and the gas trails behind like smoke from a comet. Everything is neat. Everything is consistent. This cleanness strengthens the case for non-interacting dark matter. It tells us not just that dark matter exists, but that it behaves in specific ways. All of this circles back to one fundamental truth. The bullet cluster is not just a cosmic car crash. It's a Rosetta Stone for cosmology. It is a rare natural experiment that exposes the contours of an invisible world. In this one event, the universe laid bare one of its greatest secrets, that the majority of its matter is not made of atoms, but of something else entirely. Something we cannot see. Something we cannot touch. Something that shapes galaxies, curves space-time, and drifts silently through everything. And that is only the beginning. As we dive even deeper, we find that the bullet cluster is not merely an isolated event in space. It is a cosmic narrative of scale, silence, and structure. One might look at this glowing clash of galactic systems and see chaos, but beneath the surface is an order more profound than anything we might intuitively expect. The two clusters involved in this dramatic merger weren't just randomly flying toward each other. They were guided by the fundamental scaffolding of the universe, the web of dark matter that binds the cosmos together. This large-scale structure, often referred to as the cosmic web, consists of filaments composed predominantly of dark matter, along which galaxies and clusters form and evolve. The bullet cluster, then, is not a singular event, but one junction in the colossal, interconnected spine of the cosmos. These filaments are thought to act like cosmic highways, directing galaxies and clusters to move, merge, and assemble into ever larger structures. The bullet cluster happened because two such highways intersected. The smaller subcluster came barreling down one filament, crashing headfirst into the core of the larger cluster. This explains the tremendous speed of the collision, thousands of kilometers per second, accelerated over billions of years by the gentle, persistent pull of dark matter along the filaments. This narrative only adds to the bullet cluster's relevance. It confirms not only the presence of dark matter in localized systems, but its role in shaping the overall architecture of the universe. In attempting to reconstruct the precise physics of this cosmic collision, scientists turn to hydrodynamical simulations, detailed numerical models that replicate not only the gravitational interactions of galaxies and dark matter but also the complex behavior of hot gas. These simulations use supercomputers to calculate, time step by time step, the evolution of all involved matter components during the merger. When a simulation recreates the observed positions and characteristics of the gas, galaxies, and lensing mass from the real bullet cluster, it strengthens our understanding of the underlying physics. These simulations have been instrumental in confirming that a collisionless dark matter component is necessary to explain what we see. In every test, ordinary matter alone fails to reproduce the observed features without invoking an invisible mass. Moreover, these simulations reveal that we are observing the bullet cluster at a very specific moment in time, about 150 to 200 million years after the core collision. This is crucial, because the observable offset between the hot gas and the dark matter halo only persists for a relatively short cosmological period. Eventually, the gas and the galaxies will relax into a more uniform structure, erasing the evidence of their violent past. This means that we are lucky, cosmologically lucky, to be witnessing the bullet cluster in this precise state, when the evidence is still imprinted in the sky like a fossilized burst of motion. In another few hundred million years, it may appear as just another relaxed cluster, its dynamic history buried beneath equilibrium. And what of the individual galaxies caught up in this grand collision? Contrary to what one might expect, most of them survived the encounter intact. Galaxies, after all, are mostly empty space, billions of stars spread out over tens or hundreds of thousands of light years. When two clusters collide, their galaxies generally pass right through one another without much direct interaction. It's a surreal image, trillions of suns threading through a war zone of plasma, largely unaffected. The real drama, the real violence, happens in the hot gas, the intergalactic plasma that comprises the majority of baryonic matter in the clusters. This gas smashes together, compresses, shocks, and glows in X-rays. But the galaxies? They just keep going, like ghosts through fog. And then there's the gravitational lensing. This technique, where astronomers map the distortions in the shapes of distant background galaxies caused by the gravitational field of the bullet cluster, is arguably the most important tool in this discovery. Gravitational lensing is powerful because it does not depend on the composition or state of matter. It only cares about mass. Whether that mass is visible or invisible, hot or cold, luminous or dark, lensing reveals its presence. The lensing map of the bullet cluster showed the mass concentration in a different location than the hot gas. This was the smoking gun, proof that the majority of the mass was not in the hot gas, but elsewhere, likely in a dark component that passed through unimpeded. This observation undermines competing theories that try to explain away the effects of dark matter. For instance, modified Newtonian dynamics, MOND, proposes altering the laws of gravity at large scales rather than invoking a new form of matter. But the bullet cluster is a nightmare for MOND. Since the visible matter, primarily the hot gas, lags behind the gravitational mass, no modification of Newton's laws can explain the mismatch without inventing some hidden mass. In other words, MOND breaks down under the weight of this collision. The bullet cluster is not just evidence for dark matter, it is evidence against many of its alternatives. Let's reflect on the deeper philosophical implications. The bullet cluster forces us to acknowledge that reality extends far beyond human perception. We evolved to see light, to feel texture, to hear sound. But none of those senses can detect dark matter. It's invisible, intangible, and silent. And yet, through scientific method, through indirect observation, and through clever inference, we have caught it in the act. The bullet cluster is not just a celestial object, it's a monument to the power of human cognition. It shows that we can reach beyond our biological limits and discover truths about the universe that no single person could ever see unaided. The psychological impact of this cannot be overstated. For many, science fiction has long presented invisible forces, cloaking devices, dark energies, unseen intelligences, as whimsical fantasy. But the bullet cluster is a reminder that the universe is already more fantastic than fiction. Invisible structures billions of light years away are shaping the universe and holding galaxies together. They are colliding, interacting, and evolving in ways we cannot touch but can know. That knowledge is a miracle of modern science, an astonishing convergence of mathematics, engineering, and imagination. And what does the future hold? Efforts are ongoing to study dozens more colliding galaxy clusters to build a larger statistical sample. The goal is to examine whether all such collisions show similar behavior. Are the gas-dark matter separations always consistent? Do the inferred cross-sections of dark matter interactions vary? Are there anomalies that might suggest new physics? Scientists are also pushing forward in direct detection experiments on Earth, like the LUX Zeppelin, LZ, experiment, the XCNONNT project, and others, each designed to trap a dark matter particle and make the invisible visible. The bullet cluster provides the cosmic context. It tells us what to look for. But we are still waiting for the moment we can say we've touched the invisible. And so the bullet cluster continues to speak. Not in sound, but in light. Not in words, but in curves. It speaks through gravity, through space-time distortion, through heat and mass and motion. It is a message from the deep past, a cosmic postcard mailed hundreds of millions of years ago, arriving just now, as our species looks upward and asks, "What is out there?" What is out there, indeed? The story of the bullet cluster doesn't end with its immediate observation. It ripples outward, touching nearly every field in astrophysics and cosmology. To understand the magnitude of its importance, we must delve into the scientific methods used to extract meaning from its data, the theoretical implications it has stirred across decades of dark matter research, and the questions it continues to raise about the true nature of the universe. Gravitational lensing, the phenomenon at the heart of the bullet cluster's dark matter revelation, operates by bending the fabric of space-time. When a massive object like a galaxy cluster lies between a distant source of light and the observer, it warps space in such a way that light from the background object is magnified, distorted, or even duplicated. This effect, predicted by Einstein's general relativity, has become one of the most essential tools in observational cosmology. In the case of the bullet cluster, this lensing not only highlighted mass, it betrayed mass that had no corresponding light. When the gravitational lensing map was overlaid with the X-ray map of the hot gas taken by the Chandra X-ray Observatory, a clear separation became undeniable. The mass was clustered around the galaxies, not the hot gas. This means the mass did not interact like the gas did, it passed through relatively undisturbed. And since galaxies themselves do not account for the majority of the mass in a cluster, there had to be something else traveling with them. That something else is dark matter. It's worth emphasizing just how profound this observation is. Prior to the bullet cluster, dark matter was largely inferred from rotational curves of galaxies, from the dynamics of galaxy clusters, and from fluctuations in the cosmic microwave background. While these sources painted a consistent picture, they were all based on indirect gravitational inferences in relatively stable systems. The bullet cluster, in contrast, is an active event, a dynamic collision. It allowed astronomers to separate the mass components based on their interactions, or lack thereof, providing the first truly empirical way to visualize dark matter independently of normal matter. Further studies pushed even deeper into the data. The temperature of the hot gas was measured to be over 100 million Kelvin, hotter than the core of most stars. This gas emits X-rays as it slows and compresses in the collision. Yet the gravitational lensing signal doesn't align with this brilliant X-ray glow. It instead aligns with the dim, cold swarms of galaxies. This observational mismatch is the crux of the dark matter argument. If gravity behaved differently, or if the matter we saw was all that existed, these maps would have lined up. But they didn't. And they don't. The only logical conclusion, based on our current understanding, is that most of the mass is invisible and does not interact via electromagnetism, only through gravity. This has led to increasingly refined measurements of what dark matter might be. One key parameter is the dark matter self-interaction cross-section, the likelihood that dark matter particles collide with each other. If dark matter had a strong self-interaction, we would expect it to behave more like gas in a collision, slowing down and interacting. But in the bullet cluster, dark matter passed through with almost no deceleration, implying an extremely low self-interaction cross-section. This observation places an upper limit on how often dark matter particles interact, ruling out entire classes of particle physics models that posit strongly interacting dark matter. At the same time, the bullet cluster doesn't tell us what dark matter is. It tells us what it is not. It is not baryonic, meaning it is not made up of protons and neutrons like everyday matter. It is not hot, meaning it is not composed of fast-moving particles like neutrinos. It is not strongly interacting. What remains are possibilities like WIMPs, weakly interacting massive particles, or axions, or particles predicted by supersymmetric theories. Each of these candidates has different masses, interaction properties, and production histories in the early universe. The bullet cluster serves as a litmus test. Any viable dark matter particle must explain what is seen in this cosmic collision. As such, the bullet cluster has become a benchmark against which all dark matter theories must be compared. Any model that seeks to replace or modify dark matter must also reproduce the separation seen in this system. Some modified gravity theories, such as TeVis, tensor vector scalar gravity, attempt to mimic dark matter effects through changes in gravitational laws. But these theories struggle to replicate the observed lensing pattern without introducing a dark matter-like substance anyway. In essence, even attempts to eliminate dark matter end up circling back to it in some form. The implications don't stop at particle physics. They extend into cosmological simulations of structure formation. The bullet cluster gives us a snapshot of how structure builds on the largest scales. It confirms that clusters form hierarchically, that is, through mergers of smaller groups. It tells us about the velocity of infall, the density of dark matter halos, and the dynamics of gas stripping. It reveals how galaxies are affected by environment, how their star formation might be quenched by ram pressure stripping, and how gravitational tides influence their orbits. In this way, the bullet cluster is not just a peculiar anomaly, it is a laboratory. A single, naturally occurring event from which dozens of scientific disciplines extract data. It's been studied not only in the electromagnetic spectrum but also in simulations, mathematical modeling, and as part of deep cosmological surveys like the Dark Energy Survey and the Euclid mission. Each new survey adds more layers of context to the bullet cluster's story, comparing it with other merging clusters like Abel 520 or the Musket Ball cluster, both of which present similar, but not identical, signatures. And these comparisons are revealing. In Abel 520, for example, the mass distribution is less cleanly separated from the gas, raising new questions. Could dark matter behavior change under different conditions? Are there environmental variables that affect how dark matter behaves in collisions? Or is Abel 520 evidence of something we don't yet understand, a new kind of interaction, or even a flaw in our measurements? These questions are not idle. They cut to the core of how science progresses, by finding contradictions and resolving them. The bullet cluster was once just a blip in a sky survey. Now it stands as a central piece of cosmological evidence. But it, too, will one day be joined by more detailed observations, better simulations, and perhaps even new kinds of data, like gravitational wave signals from cluster collisions or neutrino emissions from accelerated particles within the plasma. Each new method could add another piece to the puzzle. And let us not forget the awe-inspiring scale of what we're witnessing. The bullet cluster is located 3.7 billion light-years away. That means we are seeing it as it existed 3.7 billion years ago, when Earth's continents were barely recognizable, when multicellular life was just beginning to diversify. Light from this event has traveled across eons to reach our telescopes. That light has bent through gravity wells, passed through intergalactic voids, and landed delicately on detectors built by minds that evolved on a tiny rocky world. The very act of seeing the bullet cluster is a triumph of time, technology, and cosmic coincidence. As we process this signal, we find ourselves engaged in a conversation with the universe, one that transcends language and duration. The bullet cluster speaks in the universal dialect of mass and motion. It tells us that the universe is more than stars and galaxies. It is more than what we can see. There is structure beyond sight. There is order beyond light. There is something out there, something vast, unseen, and fundamental. We are only beginning to understand it. And the conversation continues, not just with the bullet cluster itself but with the vast cosmos that surrounds and contextualizes it. To understand the implications of this singular event more fully, we must dive into the historical framework that led scientists to the concept of dark matter in the first place, because the bullet cluster did not appear in a vacuum of knowledge. It was the result of centuries of growing astronomical inquiry, of clues gathered across time and space, each one shaping the lens through which this cluster was eventually observed. The origins of the dark matter concept trace back to the 1930s with Swiss astronomer Fritz Zwicky. While studying the Coma cluster, he noticed something peculiar. The galaxies within it were moving too fast. Based on the visible matter, there simply wasn't enough gravity to keep the cluster bound. By Newtonian physics, the galaxies should have flown apart. But they hadn't. Zwicky concluded that there must be some form of unseen mass, what he called dunkle materie, or dark matter, holding the system together. At the time, Zwicky's ideas were largely ignored. But the mystery lingered. In the 1970s, Vera Rubin and Kent Ford provided further evidence when they studied the rotation curves of spiral galaxies. Instead of the stars slowing down at greater distances from the galactic center, as would be expected if mass were concentrated in the luminous core, the stars maintained a constant velocity. This implied that the mass distribution extended far beyond the visible disk, again pointing to a halo of invisible matter. From Zwicky to Rubin, the case for dark matter accumulated steadily. But all of this early evidence relied on internal motions, how objects moved within gravitational systems. They suggested that something unseen was exerting a gravitational influence, but they couldn't isolate it or visualize it separately. This is what made the bullet cluster so revolutionary. It provided a direct, observable dissociation between the luminous matter, in this case, the hot gas, and the gravitational mass, revealed through lensing. It allowed scientists to see the invisible. Let's pause for a moment to reflect on the observational mechanics of how that lensing data was captured. The gravitational lensing effect comes in two flavors: strong lensing and weak lensing. In strong lensing, you might see dramatic arcs or multiple images of the same background galaxy. This requires precise alignment and very massive foreground objects. Weak lensing, on the other hand, is more subtle. It distorts the shapes of background galaxies slightly, statistically skewing their orientations in a pattern that reveals the gravitational field of the intervening mass. In the bullet cluster, the lensing signature is primarily weak but powerful in aggregate. By analyzing thousands of background galaxies and mapping their distortions, researchers created a gravitational mass map. This map showed two distinct peaks, coinciding with the galaxy distributions, not with the central, X-ray bright gas. It's important to understand how radical this was. The majority of normal, baryonic matter in galaxy clusters exists in the form of hot, X-ray emitting gas. Not stars. Not planets. Not dust. Gas. So if gravity were only responding to baryonic matter, the lensing map should have matched the gas. But it didn't. This observation alone wasn't made overnight. It required the coordinated effort of multiple telescopes, Chandra X-ray Observatory to map the gas, Hubble Space Telescope and ground-based observatories for optical imaging, and meticulous data reduction pipelines to account for noise, projection effects, and lensing distortions. The final result was a set of gravitational mass contours, like topographic maps, floating distinctly apart from the luminous matter. And this has massive implications for the future of cosmology. For one, it significantly narrows the range of viable dark matter candidates. Take, for example, MACHO's massive astrophysical compact halo objects, a once popular dark matter theory proposing that black holes, neutron stars, or faint, low-mass stars could account for the missing mass. But MACHO's are baryonic, and they would interact with gas during a collision. The bullet cluster rules them out as the dominant component. Other theories, like sterile neutrinos or axions, remain on the table, but each must now match the constraints imposed by this celestial event. Even WIMPs, once the leading dark matter candidate, face increasing scrutiny. Large-scale detectors like Xenon 1T and LUX have thus far failed to find definitive signs of WIMPs, making the bullet cluster's evidence even more vital. If direct detection continues to fall short, we must fall back more heavily on indirect evidence like gravitational lensing, galaxy rotation curves, and the cosmic microwave background. Speaking of the cosmic microwave background (CMB), it plays an essential complementary role. Measurements from missions like WMAP and Planck reveal small temperature fluctuations in the CMB, reflecting density variations in the early universe. These fluctuations require dark matter to explain their amplitude and pattern. Without dark matter, the universe's large-scale structure couldn't have formed as we see it today. The bullet cluster adds a modern, dynamic snapshot to the primordial picture painted by the CMB, connecting early universe conditions with current structure. This synthesis between past and present, between deep time and ongoing motion, is part of what makes the bullet cluster so captivating. It serves as a bridge between theoretical models and tangible, observable phenomena. And it gives cosmologists a rare, control experiment, in the wild. Two massive galaxy clusters colliding in such a way that their components separate and can be independently studied. We must also explore what simulations have to say about this event. Cosmological simulations, such as those produced by the Illustris or Millennium simulations, try to model the evolution of the universe from the Big Bang to the present day. These simulations incorporate both dark matter and baryonic physics, including star formation, gas dynamics, and feedback from black holes. To replicate a system like the bullet cluster, simulations must match not only the mass and gas separation but also the temperature, density, and velocity profiles observed. This isn't easy. Simulations must consider the angle of collision, the masses of the colliding clusters, their relative speeds, estimated to be around 4,500 km per second, and the post-collision dynamics. Interestingly, the bullet cluster appears to be a high-speed outlier. Some simulations struggle to reproduce its velocity under the constraints of the lambda CDM model, lambda cold dark matter, the prevailing cosmological model. This raises further questions. is the bullet cluster truly anomalous, or are our models missing some ingredient? Such questions have reinvigorated debates about the nature of dark matter interactions. Could dark matter have small, velocity-dependent self-interactions? Could there be multiple species of dark matter with different behaviors? Could certain dark matter particles decay or annihilate into radiation under specific conditions? Each hypothesis must be filtered through the bullet cluster lens. Does it predict the observed dissociation between gas and mass? It is this filtering function that has made the bullet cluster a touchstone in scientific literature. Since the first detailed paper in 2006, it has been cited thousands of times. It appears in textbooks, in conference presentations, in outreach videos, and in public exhibitions. Its haunting X-ray and optical overlay, showing ghostly purple clouds of gravitational mass offset from fiery red gas, has become an icon of modern astronomy. Yet with all of its grandeur, the bullet cluster remains just one system. Its story is amplified, validated, and complicated by other merging clusters. Consider MAX J0025.4-1222, another collision where lensing and gas maps are offset. Or El Gordo, a massive cluster with an even more extreme merger. Each of these systems adds nuance, offering different mass ratios, collision angles, and timescales. They allow scientists to build a statistical understanding, moving from a single case study to a cosmic census. The hope is that one day, with enough data, we can reverse engineer the invisible, use the behavior of visible matter in extraordinary events to deduce the properties of the unseen majority. The bullet cluster is more than a smoking gun. It is the trailhead of a new path in astrophysics, a route that doesn't just speculate about dark matter but begins to map its contours, trace its shadows, and define its limits. And while we continue this journey, we are reminded that the universe is a place of hidden forces. Forces that bind galaxies into spirals, cluster them into webs, and shoot them across space in high-velocity collisions. The bullet cluster shows us one of these collisions frozen in time, captured in a flash of X-rays and bent starlight. But it is not static. It is evolving. The shock front from the collision is propagating outward. The gas is cooling. The galaxies are drifting further apart. And somewhere, in the darkness, the vast halos of dark matter are merging silently, invisibly, forming a new, even more massive cluster. We cannot see this directly. But the bullet cluster has taught us to listen for gravity's fingerprint, to search for mass in the motion of light. This dynamic aftermath, the slow, silent coalescence of dark matter halos in the wake of one of the most energetic events in the universe, is what makes the bullet cluster not just an object of study, but a phenomenon of cosmic narration. Every frame captured, every photon measured, is a sentence in the story of how matter behaves when stripped of everything but gravity itself. And now, as the bullet cluster continues to evolve over hundreds of millions of years, we are left with its frozen footprint, offering insights, and yet provoking deeper mystery. But what exactly are we looking at when we gaze into the bullet cluster? When the Chandra X-ray Observatory captures those stunning images of superheated gas, glowing in hues of red and pink, we are seeing baryonic matter, the matter made of protons, neutrons, and electrons, the kind we understand. This gas, shock heated to over 100 million Kelvin during the collision, is emitting X-rays as it rushes past the cluster's gravitational center. It is incredibly dense in galactic terms, comprising the majority of the baryonic mass in a cluster. And yet, it's only a small fraction, less than 20%, of the total gravitational mass mapped through lensing. So where is the rest? That question, in the context of the bullet cluster, doesn't merely evoke scientific interest, it imposes scientific obligation. The gravitational lensing data doesn't lie. It curves our expectations. The dark matter remains intact, undisturbed by the tremendous forces that have scattered the visible gas. It's there, passing through like a ghost, unseen, untouched, yet undeniably influential. But perhaps even more fascinating than what it shows is what the bullet cluster tells us by not interacting. The non-collision of dark matter halos is arguably the most profound part of this story. Unlike the luminous gas, which crashes, compresses, and slows down due to electromagnetic interactions, the dark matter halos simply pass through one another without so much as a ripple. No shocks. No deceleration. No heating. This has led scientists to assign a critical parameter to dark matter, the cross-section for self-interaction. Essentially, how likely is a dark matter particle to interact with another dark matter particle? The bullet cluster places extremely tight constraints on this. If dark matter particles interacted even a little bit, the halos would have slowed or spread out, failing to maintain the clean separation seen in the lensing maps. But they didn't. This provides one of the strongest pieces of evidence for dark matter being collisionless, or at the very least, incredibly weakly interacting. This data has guided the field of particle physics with surgical precision. In the absence of direct detection, scientists use cosmic laboratories like the bullet cluster to whittle away at the parameter space of possible dark matter particles. WIMPs, weakly interacting massive particles, sterile neutrinos, axions, light dark matter, fuzzy dark matter, each must reconcile with the bullet cluster's empirical fingerprint. If your dark matter model predicts substantial self-interaction, it's likely wrong. If it predicts significant drag or diffusion during collisions, it's ruled out. But while the bullet cluster helps close doors, it also opens new ones. Could dark matter be part of a hidden sector? A shadow universe, composed of particles that don't interact with ours, except through gravity? Could dark matter itself be composite, made of bound states of exotic particles, similar to how protons and neutrons are made of quarks? Could there be dark atoms, dark photons, even dark chemistry? These models, though speculative, are not fantasy. They're being mathematically explored and computationally simulated in research labs around the world. In fact, the very existence of the bullet cluster demands that we push our models to account not only for what we see but for what we don't. It reminds us that visibility is not the only measure of reality. That the most massive components of the universe may exist completely outside the electromagnetic spectrum. That darkness may be more fundamental than light. And now, let's turn our attention to the actual dynamics of the collision. The term, bullet cluster, doesn't just refer to two galaxy clusters bumping into each other. It's a high-velocity collision, the smaller cluster plowing through the larger one at supersonic speeds. The bullet refers to this smaller subcluster, whose motion has created a shock front in the gas, visible in the X-ray images as a sharp edge. This shock is similar to a sonic boom, formed when an object moves faster than the speed of sound in that medium. In the case of the bullet cluster, that medium is ionized gas, and the shock moves through it at over 3000 to 4000 kilometers per second. This shock front is not just visually impressive, it is physically instructive. From its shape and size, scientists can determine the Mach number of the collision, the temperature of the gas, and even the age of the merger event. Estimates suggest the collision happened roughly 100 to 200 million years ago, a relatively recent event in cosmic terms. And here's where the story deepens. The bullet cluster gives us a snapshot frozen in time, but the universe is not still. Those two clusters are continuing to separate. The gas is settling, the dark matter halos are merging, and the gravitational potential is changing. We are seeing a merger in progress, a rare catch in the cosmic film reel. Moreover, the bullet cluster has become a Rosetta Stone for interpreting other cosmic mergers. Systems like Able 520, often referred to as the train wreck cluster, have shown more chaotic collisions, with strange distributions of mass and light. In Able 520, for instance, there seems to be a central concentration of dark mass without corresponding galaxies, a finding that some believe challenges the collisionless nature of dark matter. Others argue it's simply a more complex merger geometry. But either way, the bullet cluster becomes a benchmark, an example of what a clean, well-aligned merger should look like, against which others can be measured. This is critical, because science advances not only through bold new ideas, but through solid reference points. The bullet cluster is such a point. It's not the first evidence for dark matter. It's not the most detailed or the largest cluster. But it is uniquely persuasive because of the clarity of its separation. The alignment of its components. the synergy of its multi-wavelength observations, and its resonance with the theoretical framework of dark matter that had been steadily accumulating for decades before it. Let's step back now and consider the philosophical weight of all this. The bullet cluster, through nothing more than its existence, is telling us that we live in a universe filled with things we cannot see. That the grand structures we admire, galaxies, stars, nebulae, are but tracer particles on a vast, invisible skeleton. That the beauty of the cosmos is scaffolded by something utterly imperceptible, except through its gravitational whispers. It challenges our anthropocentric notion of truth. For thousands of years, humanity thought that what we could see defined what was real. The bullet cluster laughs at that. It whispers that truth may lie elsewhere. That the majority of the universe does not reflect our light, but bends it. That matter exists not to be seen, but to shape. And in this act of shaping, the bullet cluster becomes not just a cluster of galaxies. It becomes a gateway to the unknown. A key to unlocking the dark. A portrait of gravity at work, unmasked by light, unburdened by visibility. This is why it matters. This is why it endures. Because even in its stillness, the bullet cluster speaks. It speaks to every physicist attempting to quantify dark matter, every astronomer charting the distant reaches of space, every cosmologist rewriting our understanding of the cosmos. It tells a story not just of violence and collision, but of separation, of how the universe separates the seen from the unseen, the luminous from the latent, the ordinary from the extraordinary. In many ways, the bullet cluster is a paradox frozen in space, something we cannot touch or see directly, yet whose presence is more definite than the luminous matter we've always relied on. Galaxies pass through like ships in a silent sea, ignoring the turbulence of gas, ignoring even each other, tethered only by invisible gravity wells. And in this silence, we hear the echo of something deeper, an unseen architecture that refuses to be ignored. To appreciate the bullet cluster fully, we must return to gravitational lensing, one of the most powerful observational tools ever developed in astronomy. At the heart of this tool is Einstein's general theory of relativity, which tells us that mass bends the fabric of spacetime, and thus bends the path of light. When we observe background galaxies through a gravitational lens, their light is distorted into arcs, smeared into rings, magnified and warped by the gravitational presence of intervening mass. In the bullet cluster, those distortions were measured meticulously. Each lensing artifact recorded the subtle curvature imposed by mass that didn't shine. And when astronomers compiled the gravitational lensing maps, the result was unmistakable. Two distinct clumps of gravitational mass, aligned not with the luminous gas but with the galaxies themselves. The dark matter halos had passed through each other, unimpeded, just as the galaxies had. But the gas, the luminous plasma, had collided, slowed, and been left behind. This created the great separation. A cosmic fingerprint. A gravitational echo. Proof that something was there, something massive, non-luminous, and distinct from the baryonic matter that makes up stars and galaxies and us. And here is where the implications spiral outward into the vast body of theoretical physics. If dark matter exists, and the bullet cluster insists it does, then the standard model of particle physics is incomplete. Our most successful description of matter and forces lacks a candidate particle for dark matter. None of its known components, neutrinos, quarks, bosons, can account for what is inferred from gravitational lensing. This failure opens the door to new physics. The bullet cluster is not just a cosmic anomaly, it is a cornerstone of experimental necessity. It validates the search for supersymmetric particles. It motivates underground laboratories trying to detect WIMPs. It justifies the billion-dollar investments in particle accelerators and cosmic observatories. It breathes urgency into axion experiments, motivates lattice quantum field theory calculations, and provides boundary conditions for every hypothetical framework involving dark sectors, extra dimensions, or modified gravity. And this isn't mere speculation. In 2006, when the bullet cluster lensing maps were published, it was described as direct empirical proof of dark matter's existence. That claim sparked debate, of course. Science thrives on skepticism, but it withstood scrutiny. No modified gravity theory has yet fully explained the lensing observations without invoking unseen mass. Mann, Tevis, MOG, all have struggled. Either their parameters fail to match other observations, or they must still add some form of dark mass to fit the data. The irony is profound. Even attempts to eliminate dark matter often end up reinventing it under another name. In this way, the bullet cluster is not just a phenomenon, it's a crucible. It burns away weak theories. It forces rigor. It inspires humility. And most importantly, it anchors our cosmic understanding in something measurable. But the bullet cluster is not alone. It is the loudest, clearest voice in a growing cosmic choir. Similar systems, Max J0025.4, 1222, Able 2744, the Pandora cluster, El Gordo, and others, have shown signs of similar dynamics. Each provides a different angle, a different timing, a different scale. Some show pre-collision structures, others post-collision echoes. Together, they form a mosaic of gravitational encounters that extend and deepen the bullet cluster's lesson. And it's not just about confirming dark matter's existence. These clusters allow us to estimate its distribution, its clustering, its evolution over time. By comparing simulations to observations, scientists are constructing a dark matter map of the universe, an invisible cartography guided by lensing, by microwave background fluctuations, and by large-scale structure surveys. The bullet cluster thus becomes a pivot point in cosmology. Before it, dark matter was a theory supported by circumstantial evidence, galactic rotation curves, cosmic microwave background anomalies, structure formation inconsistencies. After it, dark matter gained a visual signature, a gravitational footprint, a place in the sky where its presence was undeniable. And what of the future? Well, the next generation of telescopes, like the Vera C. Rubin Observatory and the James Webb Space Telescope, promise even deeper insights. Rubin's wide-field lensing surveys will uncover thousands of new galaxy clusters. Webb will probe their ancient light, helping us understand not just what dark matter is, but how it has shaped the universe over time. Meanwhile, laboratories beneath mountains and inside cryogenic chambers continue the hunt for a dark matter particle. The bullet cluster reminds them what they're looking for, not in composition, perhaps, but in behavior. The next breakthrough may not come from a telescope, but from a detector catching the faintest echo of a collisionless particle, one that mimics the properties deduced from that giant cosmic crash billions of light years away. And therein lies the beauty. The bullet cluster is both an end and a beginning. It ends the era of speculative dark matter arguments, and begins the era of observationally grounded dark matter science. It ends our reliance on inference alone, and begins our journey toward discovery with eyes wide open, even if what we're seeing is invisible. So when we speak of the bullet cluster, we are speaking of more than galaxies, more than plasma, more than collisionless matter. We are speaking of a cosmic experiment, uncontrolled, unrepeatable, but perfectly timed. We are speaking of a natural particle collider on scales far beyond what Earth can generate. We are speaking of a chapter in the story of human curiosity, written not in ink, but in gravity. And as that story unfolds, the bullet cluster will remain etched into our scientific memory, not as a mystery, but as a message. And that message echoes far beyond the reaches of astronomy. It touches the core of scientific exploration, how we make sense of the invisible, how we confront the limits of observation, and how we embrace evidence even when it contradicts our expectations. The bullet cluster's gravitational lensing map, stark in its separation of visible matter and gravitational mass, is a direct visual rebuttal to centuries of assumption that light defines reality. It invites us to abandon the comfort of the visible and to believe instead in the weight of the unseen. In the broader cosmological framework, the bullet cluster stands as a data point in the larger story of structure formation. In the early universe, density fluctuations, quantified in exquisite detail by the cosmic microwave background, seeded the large-scale structure we see today. Dark matter, interacting gravitationally but not electromagnetically, began to clump first. It formed halos. These halos attracted baryonic matter, gas, dust, and eventually stars. The visible universe followed the gravitational scaffolding that dark matter built. And now, billions of years later, in the bullet cluster, we see those halos in motion. We see them colliding and continuing forward, indifferent to the hot gas glowing brightly behind them. That movement tells us not only that dark matter is there, but that it behaves predictably. It is cold, it does not move relativistically. It is collisionless, it does not interact strongly with itself, or with normal matter. These behaviors are critical constraints for particle physicists working to model what dark matter might be. Take WIMPs, for instance, weakly interacting massive particles. This class of theoretical particles fits the behavioral profile seen in the bullet cluster. They are massive enough to account for the gravitational pull, but weak enough in their interactions to pass through one another without scattering, just like the dark matter halos do in the cluster. Then there are axions, another class of dark matter candidates, hypothetical ultralight particles predicted by extensions of the Standard Model. Though they behave differently from WIMPs, their interactions, or lack thereof, are compatible with the observations from the bullet cluster as well. But the story doesn't end with possible particles. The bullet cluster challenges alternative explanations too. Modified Newtonian dynamics, MOND, a theory introduced to explain galaxy rotation curves without invoking dark matter, struggles under the weight of this evidence. In MOND, gravity behaves differently at low accelerations. That's enough to explain flat rotation curves of galaxies, but it doesn't easily explain why gravitational lensing would be strongest where there is little baryonic mass. MOND has been adapted and extended. TeVis, tensor vector scalar gravity, is one such example, but no formulation yet fully reconciles the observations from the bullet cluster without invoking some additional dark component. This is where the bullet cluster becomes more than just a data point. It becomes a testing ground, a crucible. It sharpens our theories and challenges our models. If a new theory of gravity can explain this cluster's behavior, its plasma distribution, its gravitational lensing, its separation of baryonic and dark mass, then that theory will gain legitimacy. If it cannot, it will fall by the wayside. And while the bullet cluster represents a dramatic case study, it is not unique. The universe is rich with collisions. Galaxy clusters merge frequently over cosmic timescales. Every one of those collisions is an opportunity to learn more. El Gordo, a massive cluster at redshift 0.87, shows similar signs. It too exhibits a dissociation between visible matter and gravitational lensing centers. Max J0717, another complex cluster, contains multiple merging components that challenge and enrich our models. These clusters collectively form a laboratory in the sky. We cannot recreate such collisions in any terrestrial lab. We cannot simulate them at 10 to the power of 15 solar masses or at millions of kilometers per second. But we can observe them. And in doing so, we peer into the physics of extremes, of matter under conditions we will never directly experience. The bullet cluster's relevance extends even to cosmological simulations. Large n-body simulations like the Millennium Simulation, Illustris, and Eagle depend on assumptions about dark matter behavior. Do dark matter particles interact? Do they decay? Do they cluster? The bullet cluster answers these questions observationally. It tells simulators that dark matter is cold and collisionless, at least on cluster scales. That anchors the simulations in reality. And simulations, in turn, predict what we should see. They tell us how dark matter should evolve. They help us interpret lensing maps, hot gas distributions, and galaxy velocities. They show us the possible fates of colliding clusters, whether they will merge, rebound, or fragment. And when those simulations match what we see in the bullet cluster, it confirms that our models are on the right track. But there's something poetic, too, about the bullet cluster. About its raw, violent beauty. Imagine two massive clusters, each weighing over 10 to the power of 15 times the mass of the Sun, hurtling toward one another at speeds of several thousand kilometers per second. Galaxies, sparsely distributed and small compared to the cluster's volume, pass through like ghosts. Dark matter, forming enormous halos around the clusters, glides silently through, unbothered. But the gas, oh, the gas, collides with immense force. It slows. It heats. It glows in X-rays captured by telescopes like Chandra. It leaves behind a visible shockwave, a bullet-like bow shock, that gives the cluster its name. This collision is not a quick one. It plays out over hundreds of millions of years. It changes the shape and mass distribution of the clusters involved. And it is frozen in time, from our perspective, as we see it happening over 3 billion light-years away. Light from that collision began its journey before the Earth had continents, as we know them. Before the rise of mammals. Before even the sun was halfway through its life. And yet that light reaches us now, telling us not only what happened, but what must be true about the cosmos. That is the wonder of the bullet cluster. It is not just a relic of a cosmic collision. It is a living document of the universe's deepest truths, etched not in stone, but in space-time itself. In many ways, it also speaks to the nature of science. The path of discovery is not always elegant or straightforward. Sometimes it takes a cosmic train wreck to reveal a hidden truth. The bullet cluster reminds us that the universe is not just more complex than we imagine. It is more complex than we can imagine, until evidence forces us to. So what comes next? The answer lies in the continued marriage of observation and theory. As telescopes grow more sensitive, as surveys become more detailed, and as simulations grow more sophisticated, we will find more clusters like the bullet cluster. We will map their gravitational fields. We will chart their gas distributions. We will measure their dynamics. And we will use all of it to constrain the nature of dark matter. And not just dark matter. These collisions tell us about dark energy too. The large-scale structure of the universe, the rate of cluster mergers, the dynamics of gravitational collapse, all are influenced by the cosmological constant, or whatever dark energy truly is. By studying the aftermath of cosmic collisions, we get closer to understanding the expansion history of the universe. The bullet cluster is a key part of that journey. It has already shown us that our intuitions about matter and visibility are flawed. It has reminded us that the universe does not owe us clarity, it offers only evidence. And that evidence must guide our understanding, however strange the conclusions may seem. Dark matter remains invisible, undetectable by conventional means. But it is not a ghost. It is not magic. It is matter. It has gravity. It forms halos. It shapes galaxies. It drives evolution. And it leaves its fingerprints on the sky, in lensing arcs, in X-ray emissions, in cosmic collisions. The bullet cluster is one of those fingerprints. Clear. Unmistakable. Permanent. And as we continue to study it, layer by layer, wavelength by wavelength, theory by theory, we come closer not only to understanding what dark matter is, but to understanding what the universe itself is made of. But even as the bullet cluster continues to be a guiding beacon in the study of dark matter, it also opens up a deeper realm of questioning, a philosophical dimension to our cosmological pursuits. When we look at this celestial collision, we are not just gathering data. We are confronting the fundamental nature of reality. If most of the matter in the universe is invisible and interacts primarily through gravity, then our understanding of substance, presence, and even existence itself must be recalibrated. The bullet cluster shows us that reality is not limited to what our eyes, or even our most advanced instruments, can directly detect. It tells us that truth is sometimes hidden in the shadow of light, buried in the subtle bends of space-time. This raises profound epistemological questions. What is knowledge when our primary tools, vision, touch, electromagnetic detection, are not enough? The bullet cluster stands as empirical evidence that forces us to trust the mathematics of gravitational lensing and the logic of mass-energy equivalence more than the brightness of light. It forces us to accept that there is more to the universe than meets the eye, quite literally. In practical terms, the collision also acts as a laboratory for testing particle physics. Physicists are searching for the particle or particles that constitute dark matter. They have built detectors deep underground, shielded from cosmic rays, in an effort to directly detect interactions with dark matter particles. These experiments, like LUX, Xenon, PandaX, and Super CDMS, are trying to catch a dark matter particle in the act of interacting with regular matter. So far, no definitive detection has been made. And yet, the bullet cluster sits silently above us, offering compelling, indirect proof that such particles must exist. It is as if the bullet cluster is whispering, "I'm real. I'm here. Now find me." Beyond WIMPs and axions, new theoretical possibilities continue to emerge. Some researchers propose that dark matter might be composed of sterile neutrinos, hypothetical versions of regular neutrinos that do not interact via any force except gravity. Others explore supersymmetric particles, or even entirely new frameworks such as mirror matter or fuzzy dark matter. The bullet cluster acts as a sieve for these theories. Any viable dark matter candidate must explain what we see in this cluster. And it's not just about what we see in isolation. The bullet cluster must also align with other lines of evidence, like the cosmic microwave background, large-scale structure, baryon acoustic oscillations, and galaxy rotation curves. The fact that it fits so well across these disparate observations strengthens its credibility. In a scientific landscape rife with uncertainty, the bullet cluster remains a point of convergence, a rare moment of clarity in the cosmic fog. Let's return now to the observational mechanics, because the way we see the bullet cluster is as important as what we see. The primary instruments that brought this cosmic drama into focus were the Chandra X-ray Observatory and the Hubble Space Telescope. Chandra revealed the hot intracluster gas, glowing fiercely in X-rays due to its incredible temperature. This gas, which constitutes the majority of baryonic mass in the cluster, was shown to lag behind the galaxies due to its collisional nature. In stark contrast, gravitational lensing studies, using data from Hubble and ground-based telescopes, revealed mass concentrations that did not align with the gas. Instead, they aligned with the galaxies. This mismatch was the smoking gun. If all the mass was in the hot gas, gravitational lensing would trace its location. But it didn't. It traced the dark matter, which passed through the collision untouched. Think of the elegance in this setup. The bullet cluster is not just beautiful in a scientific sense, it is beautiful in an artistic sense. Two massive entities, each vast beyond comprehension, collide in a slow-motion ballet, leaving trails of evidence in their wake. The galaxies glide forward. The gas erupts in frictional fury. The invisible dark matter continues, silent and unaffected. And we, from our tiny perch in the Milky Way, are able to see the aftermath and understand its implications. This ability to see across cosmic time and space gives us not just knowledge, but perspective. The bullet cluster lies about 3.8 billion light-years away. That means the light we are seeing left it 3.8 billion years ago. Earth was teeming with single-celled life. Dinosaurs had not yet emerged. The continents were still drifting into their current shapes. And yet that light began its journey then, carrying the story of this cosmic collision across eons to be caught by our lenses, interpreted by our minds, and folded into the narrative of human knowledge. This notion, that ancient light holds modern truths, underscores much of modern cosmology. The bullet cluster is not special because it is the only place where dark matter is evident. It is special because it shows it so clearly, in a way that defies misinterpretation. The separation between baryonic and dark matter is so distinct that any theory of the universe must account for it. And the ramifications go even deeper. The bullet cluster provides strong evidence against modified gravity theories that attempt to explain galactic dynamics without invoking dark matter. Some of these theories have been modified and refined to accommodate lensing data, but none have fully succeeded in explaining the bullet cluster's features without assuming some additional, unseen mass. This makes the bullet cluster one of the most robust observational challenges to alternative theories of gravity. In this way, the bullet cluster does more than support dark matter, it refines our understanding of gravity itself. It anchors our equations in reality. It tells us where Newton's laws fail and where Einstein's relativity reigns. It forces us to recalibrate what we mean by mass, gravity, and interaction. And yet, as with any good scientific story, the bullet cluster raises more questions than it answers. What is the true nature of dark matter? Why does it interact gravitationally but not otherwise? How did it come to be so dominant in the cosmic mass budget? Is it composed of one particle type or many? Could it decay or transform over time? Is it eternal? These are not idle questions. They are active frontiers of research, driven in part by the clues the bullet cluster has left behind. But there is something even more mysterious lurking beneath all of this. While the bullet cluster teaches us much about dark matter, it also indirectly touches on the other great cosmic mystery, dark energy. If dark matter is the unseen architect of cosmic structure, dark energy is the unseen destroyer, pulling the fabric of space-time apart. And just as the bullet cluster helps constrain dark matter models, the rate and nature of such cluster collisions can inform our understanding of cosmic acceleration. The more we study these events, the better we can map the history and future of cosmic expansion. This creates an intriguing paradox. Two things we cannot see, dark matter and dark energy, dominate the fate of the universe. And yet, thanks to objects like the bullet cluster, we can study them. Not directly. Not with our eyes. But through inference, mathematics, and relentless curiosity. In this way, the bullet cluster is a symbol of scientific perseverance. It shows that even the invisible can be known, even the untouchable can be measured, and even the unobservable can be understood. It reminds us that the universe is a grand puzzle, and every piece, no matter how faint or distant, matters. As we continue to observe the heavens, building bigger telescopes, running deeper simulations, and writing more elegant theories, we are following the trail blazed by clusters like this one. The bullet cluster is not the end of the story. It is the beginning. And what a story it is. The exploration of the bullet cluster also reveals an essential aspect of how scientific progress unfolds. It's not always about answering questions definitively, but rather refining and improving our understanding as more data becomes available. Each new piece of information forces us to rethink our assumptions and methods, encouraging the scientific community to remain open to new possibilities, even when those possibilities may initially seem improbable. The bullet cluster, in all its enigmatic splendor, serves as both a testament to the power of modern astronomy and a reminder of the limits of human understanding. It is important to recognize that the bullet cluster has not only enhanced our understanding of dark matter but also brought into sharp relief some of the limitations of the tools and methodologies we rely upon to explore the universe. This object's complex interplay of forces, dark matter, hot gas, galaxies, and gravitational lensing, has forced astronomers and physicists to confront the challenges of interpreting the universe through indirect means. The bullet cluster exists not as a simple illustration of theoretical physics, but as a vivid demonstration of the fact that we are still learning how to fully interpret the cosmic landscape. The intricacies of such a phenomenon demand attention to detail and sophisticated understanding, bridging the realms of astrophysics, cosmology, and even philosophical inquiry. As we move forward in our study of dark matter, it becomes clear that there will be more events like the bullet cluster to analyze. Clashes between galaxy clusters, gravitational lensing effects, and rich data sets from upcoming astronomical missions. Yet, despite the potential discoveries ahead, the bullet cluster will likely remain a cornerstone in the study of dark matter for many years to come. Its role in dark matter research is akin to a powerful magnet that draws attention to the ways in which unseen forces shape the universe. Beyond its significance for dark matter research, the bullet cluster invites us to think more deeply about the nature of the universe itself. Why do such enormous, energetic events exist in the first place? Why does the universe seem to allow for the creation of such massive structures, only for them to collide and interact in such a spectacular manner? What cosmic processes are at work that allow for the creation, destruction, and evolution of these galactic behemoths? The intersection of all these massive and mysterious forces, dark matter, regular matter, gravity, and electromagnetic radiation, presents an incredible challenge for scientists. It forces them to reconcile the theories they've spent decades building with the raw, unyielding data that the universe provides. With each new discovery about the bullet cluster and other cosmic phenomena, scientists must contend with the messy, unpredictable nature of reality, a reality that sometimes defies the elegant, mathematical models they create. But it is precisely this tension between theory and observation that drives progress in the sciences. As our understanding of the bullet cluster continues to evolve, new models and hypotheses will emerge, further refining our knowledge of dark matter, galaxy formation, and the universe at large. This process of refinement is not an indication of failure but of success. It is a testament to the ever-growing nature of human knowledge and our willingness to continuously seek answers, even when they remain just out of reach. As we look toward the future, the study of galaxy cluster collisions like the bullet cluster will remain central to our understanding of the cosmos. New technologies, better observational techniques, and more powerful computational models will allow us to probe even deeper into the universe's mysteries. Already, space telescopes like the James Webb Space Telescope and the future launch of the Nancy Grace Roman Space Telescope promise to provide even more precise measurements of cosmic phenomena. These advancements may eventually lead to more direct observations of dark matter, allowing us to unveil even more of the universe's hidden secrets. The bullet cluster is a symbol of the interplay between visible and invisible forces, between what we can observe and what remains elusive. It reminds us that the universe is far more complex than we can ever fully comprehend, but it also affirms that the pursuit of knowledge is not only about answering questions, but about the journey itself. Each discovery brings us closer to understanding the forces that govern the cosmos, even if that understanding remains a distant horizon, ever receding as we approach it. At the same time, the bullet cluster also acts as a cautionary tale, a reminder that the universe is full of surprises, many of which we are still unprepared for. Despite all our technological advancements, we are still at the beginning of a much longer journey. As we peer deeper into space, we are bound to encounter more mysteries that defy our current understanding. But this is what makes the pursuit of science so exhilarating. Every new discovery brings us closer to unlocking the deepest secrets of existence, and the bullet cluster serves as a shining example of the power of curiosity and the human drive to uncover the unknown. The bullet cluster is not just a cosmic collision, it is a symbol of the unknown, the unseen, and the unknowable forces that govern the universe. It challenges our current understanding of dark matter and offers a glimpse into the profound mysteries that lie at the heart of the cosmos. As we continue to study this extraordinary phenomenon, we will undoubtedly learn more about dark matter, the forces shaping the universe, and even the nature of existence itself. And in doing so, we will continue to push the boundaries of human knowledge, unveiling truths that have been hidden in the vastness of space for eons. The bullet cluster may have been a collision of two galaxy clusters, but in a very real sense, it is also a collision of ideas, of knowledge, and of scientific paradigms. It represents the ongoing struggle of humanity to understand the universe and our place within it. And as long as we continue to look up at the stars, we will keep encountering new and exciting challenges that will push us to think, question, and explore further than we ever have before. For now, the bullet cluster remains one of the most important cosmic discoveries of our time, but its story is far from over. As we continue to refine our tools, our theories, and our understanding of the universe, we will undoubtedly revisit this extraordinary event and continue to draw new insights from it. The search for dark matter, the exploration of galaxy clusters, and the study of cosmic collisions will continue to shape the future of astrophysics, and the bullet cluster will remain a guiding light in our pursuit of knowledge. As we continue to analyze the bullet cluster, one of the most intriguing questions that arises is what other cosmic phenomena might be out there, waiting for us to uncover them. Just as the bullet cluster revolutionized our understanding of dark matter, the search for similar events across the universe could unlock even greater mysteries of the cosmos. What if, beyond the bullet cluster, there are even more extreme and bizarre galactic interactions occurring in the far reaches of the universe? Could there be other objects like it, still undetected, that hold the key to answering the fundamental questions about the fabric of reality? The sheer scale of the universe means that we are just scratching the surface when it comes to understanding galaxy clusters and their interactions. Each galaxy cluster is an immense system, each with its own story and intricacies. Understanding how these vast structures collide, merge, and evolve could provide insights into the nature of gravity, the formation of galaxies, and the role of dark matter in shaping the universe. The bullet cluster, as one of the most well-studied examples, provides a roadmap for future research into these phenomena. One particularly promising avenue for future research is the application of gravitational wave astronomy. Gravitational waves, ripples in space-time caused by the acceleration of massive objects, have become a new tool for exploring the universe. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first direct detection of gravitational waves, opening up a new era of astronomy. This technology could potentially allow scientists to detect waves generated by the violent mergers of galaxy clusters, providing a new way to study these events without relying solely on electromagnetic observations. In the case of the bullet cluster, future gravitational wave detections could help clarify the role of dark matter and the physical processes occurring during galaxy cluster collisions. By studying the waves produced by such collisions, scientists may be able to gather more information about the distribution of dark matter, the nature of the hot gas, and the dynamics of galaxy interactions. These waves would carry information from the heart of the event, directly from the site of the collision, offering a unique perspective on what is happening in the deepest reaches of space. Furthermore, upcoming space missions and observatories, such as the James Webb Space Telescope, JWST, promise to provide even greater detail in our observations of galaxy clusters. The JWST is equipped with infrared technology that allows it to peer through dust clouds and observe objects that were previously hidden from view. By studying galaxy clusters in infrared, the JWST will help us observe the cooler regions of these clusters, which are often obscured in visible light observations. This capability could lead to breakthroughs in understanding the behavior of dark matter and the interactions between visible and dark components of galaxy clusters. Another exciting development on the horizon is the continued growth of computational astrophysics. As computational power increases and simulations become more sophisticated, we will be able to create more detailed models of galaxy cluster collisions and the role of dark matter. These models will allow scientists to test their theories against real-world data and refine their understanding of how galaxy clusters form and evolve. It could be through these simulations that we gain deeper insights into the complex phenomena that occurred in the bullet cluster and other similar events. Simulations of the bullet cluster itself, for instance, have shown that the interaction between dark matter and regular matter is crucial to understanding the dynamics of these collisions. When the bullet cluster collided, the hot gas in the two merging clusters interacted, creating shock waves and heating up to extremely high temperatures. However, the dark matter, which is thought to interact only through gravity and not electromagnetically, passed through the collision largely unaffected. This created the observable separation between the dark matter and the hot gas, providing the key evidence for the existence of dark matter in the first place. Simulating such events with greater precision will be key to refining our models of dark matter and its role in galaxy cluster evolution. Over time, these simulations could also help us understand how galaxy clusters evolve on cosmological timescales and how they contribute to the larger-scale structure of the universe. The bullet cluster, in this sense, serves as both a window into the past and a guidepost for future investigations into the nature of the universe. Beyond these technological and theoretical advancements, the bullet cluster also offers an opportunity to reflect on the philosophical implications of our cosmic discoveries. When we think about the universe on such a grand scale, looking at the collision of galaxy clusters, the mysteries of dark matter, and the unknown forces at play, we are reminded of how little we truly understand about the cosmos. The bullet cluster, in all its complexity, challenges us to question our place in the universe and the fundamental nature of reality itself. It forces us to confront the unknowns in a way that few other discoveries have done before. The very fact that we are able to observe these incredible phenomena at all speaks to the remarkable ingenuity and perseverance of humanity. We have built telescopes that peer across billions of light years, developed theories that explain the fundamental forces of the universe, and designed experiments that probe the most mysterious aspects of existence. Yet, for all that we have accomplished, the bullet cluster reminds us that there are still vast swaths of knowledge that remain hidden, waiting for the right questions and the right tools to unlock them. This humbling realization is part of the wonder of scientific discovery. Each question we answer often leads to even more profound questions. The bullet cluster may have helped us understand dark matter in new ways, but it has also opened up a host of new mysteries. As we continue to explore the universe, we are bound to encounter phenomena that challenge our deepest assumptions and force us to rethink everything we thought we knew. In this sense, the bullet cluster is more than just an astronomical object. It is a symbol of the journey of discovery itself. It represents the endless quest for knowledge, the willingness to confront the unknown, and the constant drive to understand the universe in all its complexity. It reminds us that even when we think we have all the answers, there is always more to learn, more to explore, and more to discover. As we continue to study the bullet cluster and similar cosmic phenomena, we are not just unraveling the mysteries of dark matter and galaxy clusters. We are participating in a broader process of discovery that shapes our understanding of the universe and our place within it. The knowledge we gain from these investigations will not only enhance our scientific understanding but will also inspire future generations of astronomers, physicists, and curious minds to continue exploring the cosmos. The bullet cluster, and the questions it has raised, will continue to resonate in the field of astrophysics for decades, if not centuries, to come. The future of dark matter research, the study of galaxy clusters, and the exploration of cosmic collisions is full of potential. As we continue to build on the work done with the bullet cluster, there is no telling what other groundbreaking discoveries lie ahead. What we do know is that the pursuit of knowledge is an ongoing journey, one that will continue to challenge our assumptions, expand our horizons, and push the boundaries of what we think is possible. The bullet cluster will undoubtedly remain a pivotal discovery in the history of astronomy and physics. It is a key to unlocking the secrets of the universe and a reminder of the profound mysteries that still await us. And as long as we continue to look to the stars, we will remain forever in awe of the infinite complexity and wonder of the cosmos. As we delve even deeper into the implications of the bullet cluster, it is important to consider how this discovery influences broader cosmological theories and concepts. The bullet cluster offers critical insights not only into the nature of dark matter but also into the structure of the universe itself. It allows us to test models of cosmic evolution, gravitational interactions, and the nature of the fundamental forces that govern the cosmos. With every new observation and analysis, we are brought closer to understanding the very mechanics of the universe. The bullet cluster story begins with the collision of two galaxy clusters, and the more we study such collisions, the more we learn about the forces at play in shaping the cosmos. These galactic mergers are not rare events, but rather, they are crucial mechanisms by which the large-scale structure of the universe is formed. By studying objects like the bullet cluster, scientists gain a window into the dynamic processes that shape the formation of galaxy clusters and the overall structure of the universe. One of the more fascinating aspects of these galactic collisions is the role of gas. During a collision like the one that formed the bullet cluster, the hot gas within each cluster interacts, creating shock waves and heating up to millions of degrees. However, this gas is just one component of the overall system. The dark matter and the galaxies themselves behave quite differently. The dark matter, which does not interact with electromagnetic forces, passes through the collision largely unaffected, while the gas and galaxies are slowed down by their interactions. This behavior creates the separation that was detected between the hot gas and the dark matter, a groundbreaking observation that has helped solidify the existence of dark matter. In studying the bullet cluster, scientists can compare how the different components, gas, galaxies, and dark matter, interact in such an extreme event. This comparison provides an incredibly detailed view of the dynamics of galaxy cluster collisions, and in turn, offers valuable data for refining our understanding of dark matter. The importance of this observation cannot be overstated, as it represents one of the first direct pieces of evidence that dark matter exists, and it provides a clear understanding of how it behaves in the context of galaxy cluster interactions. The study of such galactic collisions is integral to the larger picture of cosmic evolution. These interactions are not isolated events but rather part of an ongoing process that shapes the universe. As galaxy clusters merge and evolve, They create new structures and influence the distribution of matter across vast distances. The bullet cluster is just one example of this process, but it offers a unique look into how matter behaves in these extreme environments. In the coming years, we will likely see more discoveries of similar galactic collisions and mergers, thanks to increasingly advanced observational technologies. Telescopes like the upcoming James Webb Space Telescope will allow us to peer deeper into the universe, providing even more detailed observations of galaxy clusters and their interactions. This will help us build a more comprehensive understanding of the large-scale structure of the universe and the forces that shape it. With each new observation, we move closer to answering the fundamental questions about the composition of the universe, the nature of dark matter, and the forces that govern the evolution of galaxies and clusters. However, as exciting as these advancements are, they also pose new questions that will require further investigation. For instance, while the bullet cluster provided evidence for the existence of dark matter, it also raised new questions about its precise nature. Dark matter makes up a significant portion of the mass in galaxy clusters, yet it has remained largely invisible to traditional telescopes. Scientists are still working to determine what dark matter is made of, and whether it is composed of exotic particles like WIMPs, weakly interacting massive particles, or axions, or if there is an entirely new, as yet unknown form of matter. The nature of dark matter remains one of the most profound mysteries in physics today, and the bullet cluster serves as a critical piece of the puzzle. By continuing to study such clusters and their interactions, scientists can gather more clues about the properties of dark matter and its role in the universe. This research is likely to have far-reaching implications, not only for our understanding of cosmology but also for fundamental physics itself. The study of dark matter also ties into larger questions about the fate of the universe. As we learn more about how galaxies and galaxy clusters evolve, we gain valuable insights into the ultimate destiny of the cosmos. Will the universe continue to expand indefinitely, or will it eventually collapse in on itself? How will the forces of dark energy and dark matter interact as the universe ages? These are the kinds of questions that are at the forefront of cosmological research, and understanding the dynamics of galaxy clusters like the bullet cluster will play a significant role in answering them. Another area where the bullet cluster has profound implications is in the study of gravity. The observation that the distribution of mass in the bullet cluster is different from the distribution of visible matter suggests that gravity behaves differently in the presence of dark matter. While we have long understood gravity as described by Einstein's theory of general relativity, the bullet cluster provides an opportunity to test the limits of our understanding. If dark matter interacts with gravity in unexpected ways, it could lead to new insights into the nature of gravity itself, potentially leading to a revision of current theories or even the development of entirely new models. In addition to its implications for dark matter and gravity, the bullet cluster also helps us better understand the formation and evolution of galaxies. Galaxy clusters are among the largest structures in the universe, and understanding how they evolve and interact is crucial for understanding the broader cosmic context. The bullet cluster provides a snapshot of two galaxy clusters colliding and merging, offering a glimpse into the processes that shape galaxy formation and evolution on a massive scale. By studying the aftermath of such collisions, scientists can learn about the processes that lead to the formation of supermassive black holes, the growth of galaxies, and the distribution of dark matter. These are all fundamental questions in modern astrophysics, and the bullet cluster provides a natural laboratory for studying them. As we continue to observe more galaxy cluster mergers, we will gain a deeper understanding of how galaxies grow, how supermassive black holes form, and how dark matter influences the evolution of these massive structures. Moreover, the study of galactic mergers also has practical implications for our understanding of the long-term future of our own galaxy, the Milky Way. In a few billion years, the Milky Way will collide with the Andromeda Galaxy, a process that is expected to trigger the formation of new stars and potentially even a new supermassive black hole at the center of the merged galaxy. Understanding how galaxy mergers work, as exemplified by the bullet cluster, will help us predict the outcome of this inevitable collision and how it will affect the future of our own cosmic neighborhood. As technology advances and our ability to observe the universe improves, the importance of the bullet cluster will only grow. New instruments, such as gravitational wave detectors and next-generation telescopes, will provide even more detailed data on cosmic collisions, and the role of dark matter and dark energy will become clearer. With every new discovery, we will inch closer to understanding the true nature of the universe and the forces that govern it. The journey of scientific discovery is far from over. The bullet cluster has opened up new frontiers in our understanding of the cosmos, but there are still countless mysteries waiting to be uncovered. As we continue to study the bullet cluster and similar phenomena, we will likely make even more groundbreaking discoveries that challenge our assumptions and push the boundaries of human knowledge. The universe, in all its vastness and complexity, remains an infinite source of wonder, and the story of the bullet cluster is just one chapter in the ongoing quest to understand the nature of reality itself. As we continue our exploration of the bullet cluster, we move from the specifics of the collision itself to a broader understanding of how it fits into the ever-expanding landscape of modern cosmology. The importance of the bullet cluster extends far beyond its immediate discovery and implications for dark matter. It serves as a critical stepping stone in unraveling some of the most profound mysteries of the universe. The bullet cluster, discovered in 2006, provides an invaluable opportunity to probe the interaction of matter, dark matter, and the universe's expansion on a colossal scale. As the two galaxy clusters collided, it revealed several key pieces of evidence that we would otherwise have had difficulty observing. Notably, the bullet cluster shows us how dark matter interacts in the absence of electromagnetic forces, providing a strong observational confirmation of its existence and its separate, non-interacting nature. In addition to its role in proving the existence of dark matter, the bullet cluster has played a central role in shaping our understanding of the cosmic web. The cosmic web is the large-scale structure of the universe, where galaxy clusters and galaxies themselves are connected by vast filaments of dark matter and gas. Understanding this structure is vital to understanding how galaxies form, evolve, and eventually collide, and the bullet cluster offers a unique example of the processes at play in the universe's largest structures. The study of galaxy clusters like the bullet cluster also helps to refine our understanding of the behavior of dark energy, which is thought to be responsible for the accelerated expansion of the universe. Dark energy is a mysterious force that counteracts gravity on the largest scales, causing the universe to expand at an ever-increasing rate. Although we have not yet fully understood its nature, studying objects like the bullet cluster helps provide crucial clues to how dark energy behaves in the presence of matter. The way galaxy clusters behave in the context of dark matter, gas, and gravitational forces offers valuable information on how dark energy might influence the universe's evolution and its ultimate fate. As we move forward in cosmological research, the bullet cluster remains a linchpin for testing different models of dark matter. One of the leading theories posits that dark matter is composed of weakly interacting massive particles, or WIMPs. These particles would interact through gravity and the weak nuclear force but would not emit or absorb light, making them nearly impossible to detect directly. The bullet cluster's separation of visible matter and dark matter, however, offers a unique opportunity to explore whether such particles could be responsible for the observed gravitational effects. Furthermore, the bullet cluster has opened the door to investigating alternative models of gravity. While the standard theory of gravity, based on Einstein's general relativity, has been incredibly successful in explaining many cosmic phenomena, some researchers believe that there may be modifications to this theory that could better explain dark matter's effects. The bullet cluster's observations provide an ideal testing ground for these alternative theories, allowing scientists to compare how different gravitational models would predict the behavior of matter and dark matter during such galaxy collisions. The collision dynamics observed in the bullet cluster may help to validate or challenge existing theories of gravity. Another fascinating aspect of the bullet cluster is the way it contributes to our understanding of galaxy formation and evolution. Galaxy clusters are the largest known gravitationally bound structures in the universe, and understanding how they evolve is a crucial piece of the puzzle of cosmic evolution. By studying the bullet cluster's dynamics, we gain insights into the processes that occur when two clusters collide and merge. These processes include the redistribution of both visible and dark matter, the formation of new stars and galaxies, and the eventual stabilization of the system after the merger. By understanding these processes, scientists can better predict the future of our own galaxy, the Milky Way, which is currently on a collision course with the Andromeda Galaxy. The bullet cluster also serves as an excellent laboratory for studying the fundamental forces that govern the universe. As the collision between the two galaxy clusters unfolded, the interplay of these forces, gravitational, electromagnetic, and nuclear, created a complex web of interactions. These interactions have profound implications for understanding the laws of physics, including the behavior of matter and energy at extreme scales. The extreme conditions present in such collisions provide a unique opportunity to test the limits of our knowledge of physics. The potential for new physics and groundbreaking discoveries that the bullet cluster offers is virtually limitless. The information gathered from studying such clusters could eventually help unlock the mysteries of the universe, including the nature of the dark energy that drives its accelerated expansion. It may even help us understand the ultimate fate of the universe itself, whether it will continue expanding forever, eventually contract, or end in some other unimaginable way. Looking to the future, the role of the bullet cluster in shaping the field of cosmology cannot be overstated. The continued study of galaxy clusters, along with advancements in observational technology and analytical techniques, will undoubtedly lead to even more profound discoveries. Instruments such as the James Webb Space Telescope, as well as upcoming gravitational wave detectors, will enable us to peer even further into the universe's most distant reaches, uncovering new clues about the fundamental nature of dark matter, dark energy, and the forces that govern the cosmos. The bullet cluster has already proven to be an extraordinary cosmic laboratory, one that has helped redefine our understanding of the universe. As we continue to study this remarkable structure and others like it, we are likely to encounter even more surprises and revelations. The cosmic mysteries that the bullet cluster has unveiled are only the beginning of what promises to be a long and exciting journey into the depths of space and time. In addition to its scientific importance, the bullet cluster has also had a profound impact on our philosophical and existential understanding of the universe. The discovery of dark matter and dark energy, as well as the realization that we live in a universe dominated by invisible forces, forces us to rethink our place in the cosmos. It challenges our perception of reality and invites us to consider the possibility that much of the universe remains beyond our direct perception. The bullet cluster, in this way, has become not just a scientific discovery but a reminder of the vastness and mystery of the universe in which we exist. As we continue to push the boundaries of human knowledge, we must acknowledge that the bullet cluster represents a pivotal moment in our understanding of the cosmos. It is a symbol of the power of science to reveal the hidden forces that shape the universe and a testament to the relentless pursuit of knowledge. With each new discovery, we move closer to understanding the true nature of reality, and the bullet cluster will remain a key figure in this ongoing journey. The bullet cluster is not just a cosmic phenomenon, it is a reflection of the limitless curiosity and ingenuity of humankind. It is a reminder that even in the most distant and seemingly unreachable corners of the universe, there are still mysteries waiting to be uncovered. As we look toward the future, the bullet cluster will undoubtedly continue to inspire new generations of scientists, thinkers, and dreamers to explore the unknown and to push the boundaries of our understanding even further. The story of the bullet cluster is far from over. It is a story of discovery, of wonder, and of the unyielding human spirit to understand the universe. And as we continue to explore its mysteries, we are bound to uncover even more profound insights that will reshape our understanding of the cosmos. The bullet cluster is not just a chapter in the history of science, it is a symbol of the boundless potential of human curiosity and the eternal quest for knowledge. As we delve even deeper into the complex story of the bullet cluster, it becomes evident that its role in modern astrophysics is not just pivotal, it's transformative. Its existence has created a critical benchmark against which we can test the limits of both our observational technology and theoretical frameworks. This makes it not only a cosmic anomaly but a lighthouse guiding multiple fields of science through the fog of the unknown. The name, bullet cluster, is more than just a catchy label. It stems from the high-speed nature of the smaller subcluster, which has passed through the larger cluster like a bullet, hence the name. The term also evokes a visceral image, a supersonic cosmic object tearing through space and distorting everything in its path. This supersonic movement produces a shock wave, just like a bullet through air, which has been observed in X-ray wavelengths using instruments like the Chandra X-ray Observatory. This shock front is one of the key indicators that a major collision has occurred and helps scientists model the speeds, masses, and temperatures involved in the collision. One particularly fascinating aspect of the bullet cluster lies in its ability to separate different components of the universe in a very visual and observable way. The hot gas, which makes up the majority of the normal, or baryonic matter in galaxy clusters, interacts electromagnetically. That means when two clusters collide, this gas is slowed down, or even stopped by friction-like forces. But the galaxies themselves, along with the dark matter, pass right through one another with barely any interaction. This leads to a visible offset between the hot gas and the galaxies, something that would be impossible if all mass were only made of visible matter. To understand just how strange this is, imagine two massive clouds of fog colliding in the night. You'd expect the fog to mix and slow down at the collision site. Now imagine if, inside each cloud, a handful of birds were flying. These birds don't stop. They pass right through the other cloud of fog without slowing down. The fog represents the hot gas, while the birds represent the galaxies and dark matter. After the collision, you'd see the fog mostly piled up in the middle, while the birds have moved ahead. This bizarre visual offset, when translated into astronomical terms, tells us that most of the mass must be where the birds and dark matter are, not where the fog is. And that, in turn, becomes undeniable evidence that some form of invisible mass, dark matter, is present. What makes this even more compelling is the use of gravitational lensing to see the dark matter. Gravitational lensing is the bending of light from background galaxies as it passes through the gravitational fields of massive objects, in this case, the bullet cluster. By analyzing how much and in what way the light from more distant galaxies is bent, scientists can create a map of mass distribution. What these maps reveal is stunning. The majority of the mass is not where the hot X-ray emitting gas is, but around the locations of the galaxies themselves, which aligns perfectly with where dark matter is expected to be. Now, this discovery has massive implications because it's one of the strongest direct pieces of evidence that dark matter actually exists as a separate entity, and not just a mathematical placeholder. Up until the bullet cluster was observed in this way, there was still room for alternative explanations, such as modified Newtonian dynamics, MOND, or other tweaks to general relativity that attempted to explain galactic rotation curves without invoking dark matter. But the bullet cluster doesn't just test these theories, it breaks them. MOND, for example, has a hard time accounting for this separation of mass without invoking unseen matter. The gravitational lensing data shows mass in areas that MOND alone cannot explain. Essentially, the bullet cluster acts as a laboratory where dark matter becomes indirectly visible, not through light but through gravity itself. From this point, we can extend our investigation to even larger scales, beyond the bullet cluster and into other galaxy clusters that show similar, though sometimes less pronounced, phenomena. Take the MAX J0025.4-1222 cluster or Abell 520. These are also collision events where the separation between gas and galaxies has been observed, and though the evidence isn't always as clear-cut as with the bullet cluster, the trend holds. When taken together, these clusters help reinforce the idea that dark matter not only exists but behaves consistently across different cosmic environments. Yet, even with all this powerful evidence, we are still left with the most frustrating and tantalizing question in astrophysics: what is dark matter? The bullet cluster has proven that it's real. It exerts gravitational force, doesn't interact electromagnetically, and behaves in ways that make sense in simulations. But we don't know what it is made of. Is it composed of WIMPs, weakly interacting massive particles? Axions? Sterile neutrinos? Something more exotic, like primordial black holes or undiscovered quantum fields? Despite decades of research and entire experiments like those at CERN, the LUX detector, and the Xenon 1T project, we have yet to detect a single particle of dark matter directly. And so, the bullet cluster stands as both a triumph and a mystery, a demonstration of something we can see only through its effects, yet cannot touch or truly identify. Moreover, the bullet cluster opens up discussions around the formation and fate of galaxy clusters. Galaxy clusters are not just randomly distributed throughout the universe. They form at the intersections of massive filaments in the cosmic web, and their collisions are not only common but expected. These mergers lead to some of the most energetic events since the Big Bang, releasing enormous amounts of energy, triggering star formation, and altering the trajectories of galaxies. Understanding one such collision in great detail allows us to extrapolate the behavior of the cosmos on scales far beyond our reach. The dynamics observed in the bullet cluster are also feeding into simulations of large-scale structure formation. Cosmologists use supercomputers to create simulations of the universe, from the Big Bang to the present day, incorporating dark matter, dark energy, baryonic physics, and more. The bullet cluster becomes a checkpoint for these simulations, and observable that the simulations must be able to reproduce to be considered accurate. And as our computing power increases, these simulations are becoming increasingly detailed, making the bullet cluster not just a relic of a specific observation, but an ongoing calibration point for our most cutting-edge models. Even more fascinating is how this cosmic collision can shed light on the earliest moments of the universe. While the bullet cluster itself formed billions of years after the Big Bang, the physics that govern its behavior, particularly the interactions of dark matter, are rooted in the earliest instance of cosmic history. Some theories propose that dark matter was one of the first forms of matter to decouple from radiation shortly after the Big Bang, setting the stage for all subsequent structure formation. In that sense, the bullet cluster is not just a snapshot of a cosmic event, it's a glimpse into the universe's origin story. And yet, even with all we've learned from this cluster, its power lies just as much in what it doesn't reveal. It underscores our ignorance as much as it enlightens. It shows us that the universe is not made primarily of the matter we see and interact with every day, but instead composed of substances and energies we don't yet understand. This realization is both humbling and motivating, reminding us that science is not a body of facts, but a process, a journey. And the bullet cluster, with its mysterious shadows of invisible mass and distorted arcs of background galaxies, is one of the most powerful mile markers on that journey. The bullet cluster's influence continues to ripple through nearly every corner of cosmological research, and not just for what it reveals about dark matter, but also for how it pushes us to reconsider our assumptions about the cosmos. This astronomical event is not just a curiosity, it is an empirical cornerstone that has become part of the foundation upon which modern astrophysics rests. It challenges theoretical models, refines simulations, and invites new experimental approaches, each inching us closer to understanding the invisible threads that weave the universe together. Among the many fascinating consequences of the bullet cluster's discovery is its implication for the fundamental nature of gravity. In the 20th and early 21st centuries, physicists began to explore alternative theories of gravity in an attempt to explain galactic rotation curves and cosmic structure without relying on the elusive concept of dark matter. Modified Newtonian dynamics, Mond, Tevis tensor, vector, scalar gravity, and other extensions of general relativity sought to describe the large-scale behavior of galaxies by modifying how gravity behaves over vast distances. Yet, the bullet cluster remains a formidable obstacle for these theories. Why? Because Mond-like theories predict that the gravitational potential should be tightly correlated with the distribution of visible matter. But in the bullet cluster, the gravitational potential, mapped via gravitational lensing, clearly lies where there is little or no visible matter. This creates a devastating contradiction for these models, one that has yet to be resolved convincingly by their proponents. But the implications don't stop there. Let's consider the thermodynamics of the bullet cluster. The collision between the two clusters generated an immense shock wave through the intergalactic medium, compressing and heating the gas to temperatures exceeding hundreds of millions of degrees Kelvin. Observations from the Chandra X-ray Observatory revealed a sharply defined bow shock, much like the sonic boom of a supersonic jet. This shock front isn't just visually spectacular, it's also incredibly useful. By analyzing the temperature and pressure gradients across the shock front, scientists can calculate the velocity of the smaller subcluster. Estimates suggest it's moving at several thousand kilometers per second, nearly Mach 3 in cosmic terms. These shock waves provide data for studying how energy and entropy are distributed in large-scale cosmic collisions. They help us understand the heating processes in the intergalactic medium, the formation of magnetic fields, and even the behavior of plasma at cosmic scales. The physics of these shocks mirrors many high-energy plasma processes on Earth and in our Sun, but on a vastly larger scale. Thus, the bullet cluster serves as a bridge between small-scale plasma physics and the large-scale structure of the universe. Another fascinating avenue of study relates to galaxy evolution. When clusters collide, the interactions between galaxies are not merely gravitational. They can also trigger star formation. As the gas in individual galaxies is compressed or stripped during the collision, it can collapse into new stars, reigniting previously dormant regions of the galaxy. These so-called starburst galaxies have been observed in and around the bullet cluster, indicating that the collision was not only violent but also creatively generative, seeding new stellar nurseries throughout the cluster. This dual nature, destructive and creative, is one of the most poetic aspects of cosmic collisions. Additionally, the collision provides insight into the fate of galactic gas and how it influences the life cycle of galaxies. Ram pressure stripping, for instance, is a process wherein the interstellar gas within a galaxy is swept away as the galaxy moves through the dense intracluster medium. This strips the galaxy of its star-forming material and can effectively halt star formation, transforming a spiral galaxy into a more passive elliptical one. The bullet cluster, due to its high-speed dynamics and dense gas environment, is a laboratory for observing ram pressure stripping in action. We can see galaxies being choked off from their star-forming fuel in real time, something that deepens our understanding of galaxy transformation in dense environments. Let us now turn to the observational challenge that the bullet cluster posed and continues to pose. Capturing its data was no easy feat. It required multi-wavelength observations, from radio to optical to X-ray, and involved the cooperation of some of the most advanced telescopes on Earth and in space. The Hubble Space Telescope provided sharp optical imaging, showing the positions of galaxies and enabling precise gravitational lensing measurements. The Chandra X-ray Observatory captured the hot gas in incredible detail, revealing the bow shock and the shape of the colliding subclusters. Weak lensing maps were constructed using background galaxies as beacons, distorted by the intervening mass. Each wavelength added a piece to the puzzle, and only by assembling them all were scientists able to construct the now iconic image of the bullet cluster, with its X-ray gas offset from its gravitational center. From an educational perspective, the bullet cluster is a golden teaching tool. It elegantly shows how astrophysics is not merely theoretical but deeply observational. It demonstrates how disparate pieces of data, from light bending to X-ray spectra to optical imaging, can be layered together to reveal hidden truths. It's a poster child for scientific collaboration across institutions and nations, combining resources from NASA, the European Space Agency, and observatories worldwide. It's also a reminder of how empirical data can cut through theoretical noise, offering clarity where speculation once reigned. Another aspect that deserves deep contemplation is the philosophical dimension introduced by the bullet cluster. If we accept that most of the mass in the universe is made of a substance we cannot see or touch, something that only interacts gravitationally and perhaps via the weak nuclear force, then we must also grapple with the profound reality that our senses and our instruments are fundamentally limited. The bullet cluster is a cosmic mirror, reflecting not only the light from distant galaxies but also the limits of human perception. It reminds us that much of reality may lie forever beyond our direct observation, and that knowledge itself is always partial, always incomplete. And yet therein lies the power of science, its capacity to infer, deduce, and reveal what cannot be seen directly. By studying gravitational lensing, astronomers have found a way to see dark matter. By modeling gas dynamics, they've understood the nature of cosmic collisions. By observing galaxy transformations, they've mapped the life cycle of the cosmos. The bullet cluster is not merely a phenomenon, it is a methodology, a case study in how science advances by integrating observation, theory, and imagination. Perhaps most intriguingly, the bullet cluster continues to inspire future missions and technologies. It has informed the design of next-generation observatories such as the James Webb Space Telescope, the Vera C. Rubin Observatory, and the Euclid mission. These instruments aim to probe deeper into the structure of the universe, hunt for other examples of dark matter-dominated clusters, and improve our understanding of cosmic evolution. The bullet cluster is a singular event, but it has opened a door to an entire class of phenomena, violent mergers, dark matter mapping, plasma dynamics, that are now central to astrophysical inquiry. The bullet cluster is not just an observational marvel. It is a crucible where multiple lines of scientific inquiry intersect. It stands at the crossroads of cosmology, plasma physics, gravitational theory, and galaxy evolution. Its impact has reverberated through textbooks, simulations, and scientific conferences. It has humbled theorists, emboldened observers, and challenged skeptics. It is a reminder that even in the cold, dark expanse of space, where collisions unfold over billions of years and across millions of light years, clarity can emerge. And when it does, it lights the path forward, not just for science, but for humanity's quest to understand its place in the cosmos. The bullet cluster, despite being only one among countless galaxy clusters, continues to be disproportionately important in shaping our understanding of the cosmos. As we journey deeper into its scientific implications, one cannot ignore how it revolutionizes the way we view the interplay between visible and invisible matter. In a universe where the vast majority of mass is unseen, the bullet cluster stands as a singular event that renders the invisible visible. But how exactly does it achieve that? The answer lies in its rare combination of clarity, violence, and separation of components. In most galaxy clusters, baryonic matter, normal matter made up of atoms, accounts for only about 10 to 15% of the total mass. The rest is presumed to be dark matter. However, under normal, undisturbed conditions, dark matter and baryonic matter are largely overlapping. This makes it nearly impossible to distinguish between what is influencing gravitational forces and what is emitting or absorbing radiation. The bullet cluster changed this paradigm by providing a rare moment of separation between those two constituents during a high-speed collision. During this collision, the stars, due to the immense distances between them, pass through one another with minimal direct interaction. The dark matter halos, not colliding electromagnetically, also continued relatively unimpeded. But the hot gas, which constitutes most of the visible baryonic matter in clusters, did not pass through so easily. It collided violently, slowed down, and heated up, generating intense X-ray emissions that Chandra captured in high detail. This spatial separation between the dark matter, mapped by gravitational lensing, and the hot gas, seen in X-ray imaging, is what gave the bullet cluster its legendary status. It made the dark matter stand apart. This visualization was a shock to many. For decades, dark matter had remained a hidden, inferred presence. But now we could see it, not directly, but through its effects on light and space itself. The images of the bullet cluster essentially depicted a ghost, a massive gravitational entity that could not be accounted for by visible matter alone. This single image became the clearest evidence that dark matter was not just a mathematical fix for strange galactic rotation curves, but a real, physical component of the universe with measurable influence. Now let's dive even deeper into the lensing effect that made this possible. Gravitational lensing relies on Einstein's general theory of relativity, which tells us that mass warps spacetime. Light, though massless, travels through this curvature and is deflected as if it were passing through a lens. When we observe a massive structure like the bullet cluster, we see background galaxies whose images are subtly stretched and distorted by this lensing. By analyzing thousands of these distortions statistically, scientists can reconstruct a detailed map of the mass distribution in the foreground cluster. In the bullet cluster, this mass map did not align with the X-ray emissions. Instead, it aligned with the galaxies and the presumed locations of dark matter halos. The shock front and the displaced gas trailed behind. This mismatch between visible matter and gravitational influence is what debunks many modified gravity theories. The bullet cluster, in essence, decoupled gravity from light, a revelation that sent ripples through theoretical physics. But we must not overlook the human side of this discovery. The collaborative effort that led to the bullet cluster's mapping involved astronomers, physicists, software engineers, data scientists, and technicians across continents. It required intricate coordination between space-based observatories like Chandra and Hubble and ground-based telescopes. Data had to be calibrated, cross-referenced, modeled, and interpreted, often involving months or years of computational analysis. This wasn't just a scientific breakthrough, it was a triumph of human cooperation in pursuit of truth. On a broader scale, the bullet cluster has become a benchmark for identifying and interpreting other merging galaxy clusters. It taught scientists what to look for: separation of gas and mass, shock fronts, bow shocks, lensing signals, and disturbed morphologies. Since its discovery, other clusters have been studied in a similar fashion: Max J0025, Able 2744, and El Gordo among them. Each presents its own variations in mass ratio, velocity, viewing angle, and stage of collision. But none have matched the clarity or evidentiary power of the bullet cluster. The bullet cluster also raises deep questions about the fundamental structure of dark matter. What kind of particles compose it? Why do they interact so weakly, even during the violent merger of galaxy clusters? If dark matter can sail through dense gas and gravitational chaos unscathed, does this imply it is entirely collisionless, or merely weakly interacting? These are not trivial questions, they probe the edge of known physics. One of the most promising avenues for understanding dark matter is through simulations. Astrophysicists use supercomputers to create simulations of galaxy cluster collisions under different dark matter scenarios: cold dark matter, warm dark matter, self-interacting dark matter, and others. These simulations are then compared to real observations like those of the bullet cluster. If the real-world collision matches a particular simulation, it lends credence to the associated dark matter model. This comparative approach has become a core strategy in modern cosmology. Cold dark matter models, which assume slow-moving, collisionless particles, align well with the bullet cluster's behavior. The dark matter halos pass through one another without noticeable scattering. In contrast, if dark matter were self-interacting to a significant degree, we would expect some drag or lag, an effect not observed here. This constrains the allowable cross-section for dark matter self-interactions, narrowing the parameter space for viable models. In short, the bullet cluster not only confirms dark matter exists, it shapes our understanding of what it is and what it isn't. Even the velocities involved in the bullet cluster are intriguing. The estimated relative velocity of around 4,500 km per second was surprisingly high, prompting questions about the cosmological implications. Are such high-velocity collisions common? Or does this event indicate some rare anomaly in the distribution of mass and energy? If the latter, it could imply that our models of cosmic structure formation are incomplete or missing some important detail. Again, the bullet cluster is not an endpoint. It is a starting point for deeper questions. Another dimension to explore is how the bullet cluster fits into the larger cosmic web. Galaxy clusters like this one don't exist in isolation. They reside at the intersections of filamentary structures that thread the universe. These filaments are vast, spanning hundreds of millions of light years, and composed mostly of dark matter. The bullet cluster is likely part of such a filament, and its collision may have been shaped by the gravitational flows along these dark highways. Understanding the cluster's motion in this context could help map the invisible scaffolding of the universe. Moreover, the future of the bullet cluster remains an open chapter. In the coming billions of years, the two subclusters will continue to interact gravitationally, eventually merging into a larger, more relaxed structure. The residual effects of their collision, the stripped gas, the altered galaxy trajectories, the distorted gravitational field, will fade into equilibrium. Future astronomers may look back and only see a single massive cluster, unaware of the dramatic collision that created it. This underscores the importance of capturing and studying such events while they are dynamically active. These are fleeting windows into the processes that shape the universe. On a philosophical level, the bullet cluster confronts us with our limitations and our potential. We are tiny, carbon-based beings on a pale blue dot, using finely tuned instruments to study phenomena occurring 3.8 billion light-years away, involving forces and masses beyond our comprehension. And yet, from this distant collision, we derive insights into the fundamental nature of matter, gravity, and the evolution of the cosmos. The bullet cluster is a testament to the power of curiosity, collaboration, and scientific rigor. It whispers to us from across the universe, saying, "Look deeper. The truth is there, if you are willing to find it." And so we continue this deep voyage into the cosmos, through the lens of one of the most enlightening astronomical discoveries of our time, the bullet cluster. While we've already delved into the mechanics of its collision, the mapping of its gravitational lensing, and its role as evidence for dark matter, there remains much more to uncover. To understand the full reach of its significance, we must now turn to how it challenges existing theories, inspires new physics, and compels us to reimagine the invisible scaffolding of the universe. One of the most profound impacts of the bullet cluster has been on the debate between dark matter and modified gravity. For decades, scientists who were skeptical of dark matter's existence proposed alternative explanations for the observed phenomena in galaxies and clusters, chief among them, modified Newtonian dynamics, MOND, and its relativistic extensions like Tevis, tensor, vector, scalar gravity. These theories suggest that the laws of gravity themselves need to be altered at cosmic scales, especially where accelerations are very low, as they are in the outskirts of galaxies and galaxy clusters. Mond was particularly adept at explaining flat galactic rotation curves without invoking additional unseen mass. But it struggled with clusters. And the bullet cluster was its most damning challenge. In the Mond framework, where all gravitational effects are attributed to visible matter under a modified force law, the separation of gravitational lensing from visible baryonic matter, as seen in the bullet cluster, should not be possible. The gravity should follow the mass that emits light and gas, but it clearly doesn't. The lensing map lines up with the invisible mass, not the X-ray luminous gas. This inconsistency forced Mond proponents to concede that some form of unseen matter might still be required. Tevis, an extension of Mond meant to reconcile it with relativistic frameworks, tried to account for lensing phenomena, but even it could not fully reconcile the observed features of the bullet cluster without adding dark matter back into the equation. In essence, the bullet cluster did what few theoretical models could: it cornered the alternative. It forced a reckoning within modified gravity circles that dark matter might not just be a placeholder for broken physics, it might be something real. But this wasn't just a victory for the cold dark matter paradigm, it was also a refinement moment. The bullet cluster didn't just support dark matter's existence, it helped sharpen our picture of it. Based on how the dark matter halos pass through one another, scientists placed constraints on how much dark matter particles can interact with each other. These constraints were significant. If dark matter had strong self-interactions, it would have left observable trails or shown signs of scattering. But it didn't. The dark matter moved as though it barely noticed the collision at all, implying it is largely, if not entirely, collisionless. This brings us to the different candidates for what dark matter might be. The bullet cluster, by helping constrain dark matter's self-interaction cross-section, rules out a variety of exotic particles. For example, warm dark matter, particles with higher thermal velocities, tends to suppress small-scale structure formation and doesn't match with observed cosmic patterns as well as cold dark matter does. Self-interacting dark matter models require particles to have non-negligible interactions with each other, which again doesn't align with the bullet cluster's clean separation of mass and gas. Then we have the hypothetical particles like WIMPs, weakly interacting massive particles, which have been the frontrunners in the dark matter race for decades. WIMPs naturally arise from extensions to the standard model of particle physics, like supersymmetry, and are consistent with being both massive and weakly interacting. Their properties closely resemble the behavior observed in the bullet cluster, massive enough to exert gravity, yet invisible and non-interacting with ordinary matter or with themselves in any noticeable way. Another candidate, though more recently gaining attention, is the axion, a very light particle that interacts only through gravity and the strong nuclear force in some models. Axions also satisfy the properties of being cold and collisionless, and experiments are ongoing to detect them via their potential to convert into photons under specific magnetic conditions. Yet neither axions nor WIMPs have been directly detected, despite large, expensive, and technologically advanced experiments designed to find them. And that's where the bullet cluster holds its quiet power. Even without a direct detection, it reminds us that dark matter's gravitational fingerprint is real and persistent. The bullet cluster also has implications for how we understand the large-scale structure of the universe. Clusters of galaxies are the most massive gravitationally bound structures in the cosmos, and their collisions are rare, high-energy events. The study of such clusters gives us insights into the processes that have shaped the universe from its earliest epochs. By understanding the dynamics and aftermath of the bullet cluster's collision, scientists can refine their models of cosmic evolution. Simulations of the bullet cluster's collision show a remarkable fit to observed features, reinforcing the accuracy of our understanding of gravitational physics and dark matter behavior. These simulations require millions of particles representing dark matter, gas, and stars, all interacting under known physical laws. Matching these simulations with reality is not trivial. It involves tuning initial velocities, angles of impact, mass ratios, and thermodynamic properties of the gas. And yet, with the right parameters, the resulting virtual bullet cluster looks almost identical to the real one. This kind of fidelity gives scientists confidence in their broader cosmological simulations. When these models are scaled up, they form the cosmic web, a vast structure composed of filaments of dark matter and galaxies. These filaments stretch across hundreds of millions of light-years and intersect at nodes where galaxy clusters like the bullet cluster form. Understanding how the bullet cluster formed, moved, and collided within this web gives insight into how the universe organized itself over 13.8 billion years. But even beyond the science, the bullet cluster has sparked a kind of cultural significance within the scientific community. It is often cited in lectures, textbooks, and academic debates as a definitive observational pillar for dark matter. It's frequently used in public science communication as a simple visual demonstration of how we can see the invisible. That striking composite image, with galaxies like tiny gems, hot gas glowing in pink from X-rays, and the gravitational lensing map in ethereal blue, has become a symbol of modern cosmology. It also highlights the role of multi-wavelength astronomy. Without combining optical data to map the galaxies, X-ray data to locate the gas, and lensing analysis to find the mass, the bullet cluster would remain a confusing smudge of light in the sky. Its full meaning only emerges when we stitch together these different observational threads. This is how we truly unveil the structure of the universe, not through one lens, but through many. And the journey doesn't end there. The principles and discoveries extracted from the bullet cluster have inspired a new generation of cluster studies. Scientists now actively search for bullet-like clusters across the sky, merging systems where gas and mass are separated. Each new discovery adds data points to the growing understanding of how dark matter behaves, how clusters grow, and how structure assembles on the grandest scales. As technology advances, so too will our capacity to examine such phenomena in even greater detail. The James Webb Space Telescope, for instance, with its deep infrared capabilities, can study the galaxies within clusters at greater distances and with higher resolution. Future X-ray observatories, like Athena and Lynx, will provide even sharper images of the hot gas. And gravitational lensing maps will become more precise with upcoming surveys like those planned for the Vera C. Rubin Observatory and the European Space Agency's Euclid mission. What's more, there is the tantalizing possibility that new physics lies just beyond what the bullet cluster tells us. Perhaps dark matter is not just one type of particle, but a spectrum. Perhaps its interactions are more subtle, varying with energy or time. The bullet cluster may be just one piece of a much larger puzzle, one that, when completed, may force a revision not only of our models of matter but of the universe itself. And so, we continue to look deeper, not only at the bullet cluster but at the sky in all directions, seeking the faint trails of invisible giants whose gravity sculpts the stars. The bullet cluster is a milestone, a lens, a revelation. And though its cosmic collision occurred billions of years ago, its impact on our understanding continues to expand, just like the universe it inhabits. As we dive even deeper into the profound implications of the bullet cluster, it becomes evident that this colossal cosmic event is far more than a spectacle of galactic collision. It is a portal into the universe's hidden architecture. When we peel back the layers of what the bullet cluster reveals, we're not just looking at how two clusters collided. We're peering into the nature of matter itself, how it behaves, how it binds, and how it shapes everything we see. A key element worth exploring further is how the bullet cluster serves as a benchmark for the interaction cross-section of dark matter. By observing how the dark matter halos of the two clusters pass through one another essentially unimpeded, astrophysicists were able to place upper limits on how often dark matter particles interact with each other. This constraint is quantified by the self-interaction cross-section per unit mass. The upper limit determined from the bullet cluster is on the order of 1 square centimeter per g, a surprisingly low number that implies dark matter is not only invisible but also extremely aloof. It hardly even interacts with itself. This detail, though seemingly minor, carries enormous theoretical weight. If dark matter had significant self-interactions, we would expect to see the dark matter halos slowing down, heating up, or otherwise behaving differently during the collision. We don't. This singular fact rules out many dark matter models and narrows the search for the true nature of these elusive particles. It's like filtering an infinite ocean of possibilities down to a concentrated stream. The bullet cluster does that for us. It sharpens the lens. But to fully appreciate this constraint, we need to understand how it's derived. Observations of the bullet cluster rely on intricate gravitational lensing analysis, mapping how background light from even more distant galaxies is bent as it travels through the distorted spacetime around the cluster. This lensing effect produces measurable distortions known as shear in the images of background galaxies. By compiling these distortions across a wide field, scientists can reconstruct a two-dimensional map of the mass distribution. It's a delicate process, requiring both precise image analysis and an understanding of how light behaves in curved spacetime. What's extraordinary is that this lensing map doesn't just tell us where the mass is, it tells us what kind of mass is where. The gas, which is luminous in X-ray observations, is dragged behind during the collision. It's slowed by ram pressure, like a swimmer pushing through a pool. But the gravitational mass, mapped via lensing, surges ahead, untouched. This differential motion between gas and mass is the fingerprint of dark matter. It's as if the visible matter was slowed by friction, while the dark matter passed through like a ghost. Now imagine trying to explain that with modified gravity theories. Mond and its relativistic cousins were formulated primarily to address galaxy rotation curves, not the aftermath of violent galactic collisions. The bullet cluster breaks the predictive power of these theories. It's not just that Mond fails to explain where the gravitational potential lies. It's that it fundamentally cannot separate mass from baryons in the way the bullet cluster demands. In Mond, gravity is a direct function of visible matter. But in the bullet cluster, the gravitational pull is clearly offset from the visible gas. This mismatch is not a small error, it's a fatal contradiction. That's why even some of Mond's earliest proponents have admitted that additional dark components must exist in such systems. In attempting to preserve modified gravity, they've been forced to concede to something very similar to dark matter. This turns the original premise on its head. If you need invisible matter to make modified gravity work, then why not just accept that dark matter exists and move forward with the cosmological model that continues to succeed on every scale? Let's pivot to another layer of the bullet cluster's importance, its pedagogical power. This cluster is not just for professional astrophysicists, it has become a foundational teaching tool. In classrooms around the world, professors show that iconic composite image, the pink clouds of hot gas and the ghostly blue halos of dark matter, and they explain how we know what we know. It's a visual story that even a curious high schooler can grasp. And in an era of abstract concepts like inflation, quantum fields, and entanglement, the bullet cluster stands as a rare, tangible pillar of modern physics. In fact, if you were to design a single observational object to convince a skeptical public of dark matter's existence, the bullet cluster would be your Exhibit A. You can't see dark matter, but you can see what it does. And in the bullet cluster, its effects are as plain as a shadow on the ground, silent, but undeniable. And yet, this raises another fascinating dimension. What is dark matter, beyond its gravitational influence? If we accept its presence, what are we really accepting? The leading candidates, WIMPs and axions, remain hypothetical. We've built vast underground labs, like the Xenon 1T experiment in Italy or the LUX Zeppelin detector in South Dakota, designed to catch a rare dark matter particle interacting with a xenon atom. So far, they've found nothing conclusive. At the same time, astronomical surveys continue to hunt for indirect evidence. Gamma-ray telescopes look for faint emissions from dark matter annihilations. Radio telescopes search for axion-photon conversion signatures. The bullet cluster gives us a mass map, but the particle identity remains hidden behind that map. This ongoing search is not just a scientific puzzle, it's a generational endeavor. Finding dark matter would not only answer one of the most fundamental questions of our time, it would open the door to new physics beyond the standard model. It could provide insight into supersymmetry, extra dimensions, or even the nature of space and time itself. And the bullet cluster, with its cosmic signature, is one of the loudest voices calling us forward. Still, some scientists have proposed that perhaps we are missing something deeper. What if dark matter is not a particle at all? What if it's an emergent phenomenon, something that arises from the geometry of space-time or quantum entanglement across cosmic scales? These are speculative ideas, but they illustrate how far the bullet cluster has pushed the boundary. Because it doesn't just support the dark matter hypothesis, it demands it. And any new theory must still pass through its filter. In practical terms, the bullet cluster has also influenced how we structure our surveys. Observatories like Chandra, which revealed the X-ray gas, and Hubble, which mapped the galaxies and lensing, have become templates for future instruments. We now know that to understand galaxy clusters, we must observe them in multiple wavelengths. Optical, X-ray, infrared radio, microwave, all of these revealed different layers of the structure. The bullet cluster taught us how to synthesize those layers into a coherent picture. This lesson will be applied again and again with future projects. The Vera C. Rubin Observatory will map billions of galaxies, tracking how dark matter clusters over time. Euclid, launched by the European Space Agency, is designed specifically to measure the geometry of dark matter and dark energy in the universe. And NASA's Roman Space Telescope will deepen our understanding of gravitational lensing with unprecedented precision. All of these missions, in some way, trace their heritage back to the insights born in the wake of the bullet cluster's collision. But perhaps the most humbling realization from the bullet cluster is this: we are still at the beginning. The universe is vast beyond comprehension, and the more we learn, the more we realize how much we don't understand. The bullet cluster is not a conclusion, it is an opening. An invitation to ask deeper questions, to look farther, and to build instruments capable of catching whispers in the dark. In this galactic collision, billions of light years away and billions of years ago, the universe has given us a message. Not in words but in mass. Not in sound, but in silence. A message written in gravity, decoded by photons, and interpreted by minds that dare to ask, what holds everything together? We are not finished asking that question. And the bullet cluster, frozen in its cosmic aftermath, continues to whisper the answer. The bullet cluster remains an icon not only because of what it shows, but because of how sharply it draws the lines between what we know and what we don't. Its very structure is a cosmic paradox resolved only by the acceptance of dark matter. As we've explored, the offset between the hot gas and the gravitational mass distribution is not a minor detail, it's the critical axis upon which modern cosmology pivots. This one cluster, stitched together from light and mass and theory, pushes the scientific community into deeper territory, forcing us to refine, to discard, and to rediscover what we thought we knew. But to fully grasp the weight of the bullet cluster's implications, we need to dig into the mechanisms behind gravitational lensing even more deeply. The type of lensing used to map the dark matter here is called weak lensing, where the light from background galaxies is distorted ever so slightly by the gravitational potential of the cluster. These distortions are not dramatic like the arcs and rings seen in strong lensing, but they are pervasive. With enough background sources, scientists can statistically determine the average direction and strength of the shear, like revealing the pattern of ripples by examining floating leaves on the surface of a pond. It is from this statistical ballet of distant galaxies that the invisible structure of dark matter emerges. And when it does, it shows us something extraordinary. The mass doesn't follow the luminous gas, but the galaxies themselves, which are mostly made up of dark matter. This separation, revealed only through the lensing signal, is not a matter of interpretation. It's a result that is repeatable, observable, and in stark conflict with any model that ties gravity strictly to luminous matter. Consider, then, the sheer range of physics this touches. On the one hand, we are dealing with general relativity, Einstein's geometric theory of gravity, where spacetime is curved by energy and mass. On the other, we are forced to confront particle physics, in the desperate search for the actual particles that make up dark matter. Somewhere, a bridge must be built between these two pillars of physics, the large-scale curvature of the universe, and the microscopic quirks of subatomic behavior. The bullet cluster sits at the foot of that bridge. It does not explain everything, but it demands that an explanation must be found. It's also worth highlighting the enormous computational and observational coordination that goes into studying an object like the bullet cluster. This isn't just about pointing a telescope and taking a picture. It's about building a mosaic from X-ray observatories like Chandra, optical imaging from Hubble, spectroscopic redshifts from ground-based surveys, and weak lensing reconstructions derived from algorithms that must filter out noise, correct for atmospheric distortion, and account for every possible bias. Each of these data streams is a complex pipeline of its own, and all of them must converge coherently to produce the maps and conclusions that we've seen. There's a poetic elegance in this. In the wake of one of the universe's most violent events, the collision of two galaxy clusters, humans have built a toolkit sensitive enough to weigh the invisible. We've taken the most chaotic events and used them to clarify the rules of existence. In that chaos, we have found a signal. And in that signal, a truth. Let us then ask, what if there were no dark matter? What alternative physics would we need to explain what the bullet cluster shows us? We would need a theory where gravity behaves one way in galaxies, but another way in colliding clusters. We'd need a theory that knows how to decouple mass from light in precise, location-specific ways. We would need to rewrite the rules of gravitation such that they produce the exact gravitational lensing signature we observe, while leaving no trace in all the other systems that already agree with dark matter predictions. And we would need to do all of this without any particle-like matter contributing to the gravitational potential. No such theory exists. At least, not one that is consistent with both observational data and theoretical rigor. And that is why the bullet cluster stands undefeated as the strongest visual and empirical proof of dark matter's existence. Yet, even with all we've said, the bullet cluster is only one system. Scientists are careful not to hang a theory on a single case, no matter how compelling. This is why multiple other colliding clusters have been examined, like Max J0025.4-1222, often dubbed the baby bullet. These systems, too, show similar offsets between baryonic and gravitational mass. But the bullet cluster was the first, the cleanest, and the most iconic. It crystallized the mystery into a form we could observe and understand. And because of that, it continues to occupy a special place in the story of cosmology. Its legacy ripples out in all directions. It influences how we design instruments. It inspires how we teach dark matter. It challenges how we think about gravity. And it will continue to do so as we enter an era of deeper, more sensitive surveys. Future telescopes will study thousands of clusters. They will find new collisions, new offsets, and perhaps even subtle variations that tell us more about dark matter's behavior. We may even uncover the first deviations, signs that dark matter is not entirely passive, but interacts faintly, subtly, with itself or the baryonic world. Should that happen, the bullet cluster will have been the first whisper. And we will remember it not just as a mystery, but as the moment the cosmos cracked open and revealed the shadows behind the stars. And as we continue to peel back the layers of this cosmic onion, the bullet cluster serves not merely as a visual anomaly or even just a pivotal discovery, but as a philosophical provocation. What we see in the skies compels us to ask, what is real, and what is only visible? What is the universe made of when most of its mass lies in darkness? The bullet cluster, in essence, is a confrontation. It says to us, you see galaxies and gas, but that is not all there is. You must learn to see in other ways, through gravity, through distortion, through heat, through inference. This theme of inference is critical. In science, especially cosmology, we often cannot touch or isolate our objects of study. We are observers, not participants. And yet, with tools of extraordinary sensitivity and methods of staggering complexity, we deduce the invisible. In the case of the bullet cluster, this meant seeing gravity itself act independently of visible matter. It meant watching galaxies drift through each other like ghosts, while their interstellar gas slammed together like waves against stone, and then watching the gravitational lensing refuse to follow the gas. Let's pause to understand that in more depth. Galaxies in these clusters are mostly empty space. When two clusters collide, the stars in individual galaxies almost never hit each other. They pass through because the scale of interstellar space dwarfs the sizes of the stars. But the gas, the hot, X-ray emitting plasma, interacts violently. It crashes, it heats up, it slows down. This is the luminous matter. This is what you can see with a telescope. And yet, when you analyze the lensing data, the gravity does not follow the gas. It follows the galaxies, the dark matter halos, which simply pass through each other with minimal interaction. The separation is stark, measurable, and impossible to explain without invoking non-baryonic matter. This is not a one-off glitch in the data. The separation has been measured with confidence. Multiple reconstructions of the lensing field have yielded consistent results. Independent teams, using different algorithms, have confirmed the offset. The system has been observed in various wavelengths, from X-ray to optical to radio. All the stories converge on the same conclusion: what is bending the light is not the hot gas, but something else. And that something else is dark matter. Let's return to weak gravitational lensing, because it's the engine that powers all of this. At its core, weak lensing requires a statistical analysis of thousands of background galaxies. Each galaxy's shape is slightly distorted by the gravitational potential of the matter in the foreground. By measuring the average distortion in different directions across the sky, scientists build a map of the gravitational field. This is not just an outline, it's a fully three-dimensional mass map. The precision required is phenomenal. The distortions are subtle, often less than 1% of a galaxy's shape, and yet, over enough galaxies, the signal emerges. The bullet cluster's mass map, constructed in this way, reveals two distinct clumps of matter that correspond to the galaxies in each cluster, not the gas. This is why the bullet cluster is not just another data point, it is a litmus test. It divides the cosmos into two camps, those theories that can account for this behavior, and those that cannot. MOND, modified Newtonian dynamics, fails this test. While MOND has had some success explaining galactic rotation curves without invoking dark matter, it struggles with systems like the bullet cluster. That's because MOND ties gravity too tightly to the distribution of visible matter. And here, in the bullet cluster, the gravity is decoupled from the baryons. MOND and similar theories have tried to evolve, some adding vector fields, others invoking complex tensors, but the data from the bullet cluster remains a brutal filter. Most alternatives do not survive it. And so, dark matter stands. Not because we have seen it directly, but because it explains what we do see. Because it provides a consistent, testable, falsifiable framework. Because, when we build simulations of cluster collisions using dark matter, they reproduce what we observe. The lensing maps. The X-ray emission. The galaxy velocities. The timing of the merger. The morphology of the shock front. All of it. The bullet cluster has also shaped our understanding of dark matter's interaction properties. If dark matter interacted with itself via strong forces, it would not have passed through the collision so cleanly. Instead, it would have clumped or scattered. The clean separation observed implies that dark matter is, at most, very weakly self-interacting. This constrains the cross-section for dark matter self-interactions, helping theorists eliminate large swaths of parameter space. This is how a single cosmic event affects the design of detectors buried beneath mountains or floating in space. It tells physicists what to look for, and what not to waste time chasing. And the bullet cluster's influence extends even further. It plays a role in dark matter annihilation studies. If dark matter particles can annihilate each other, they would produce gamma rays. By looking at the densest parts of clusters like the bullet cluster, researchers can place limits on the annihilation rate. These limits, in turn, constrain theories about what kind of particles dark matter might be: WIMPs, axions, sterile neutrinos, or something else entirely. Now consider this: everything we've discussed so far has come from light. From photons. The bullet cluster is, in every sense, a story told through light. X-rays from hot gas. Optical light from galaxies. Infrared emissions from dust. And the bending of light from background galaxies. Light reveals the structure. But the light is not the structure. That is the paradox. And that paradox fuels the next generation of astronomy. The James Webb Space Telescope, the Vera Rubin Observatory, Euclid, the Nancy Grace Roman Space Telescope, all of these missions are being designed, in part, to study dark matter and lensing in unprecedented detail. They will find new bullet clusters. New systems with even better geometry, better data, deeper lensing fields. And with each one, we get closer to mapping the dark. But we must also remember that every answer brings new questions. What is dark matter made of? How does it behave on subgalactic scales? Does it clump? Does it decay? Does it interact in ways we haven't yet imagined? The bullet cluster gives us constraints, not a composition. It shows us what dark matter is, not what it is. And that distinction matters. In many ways, the bullet cluster is a doorway. Beyond it lies the realm of the unknown. A realm where galaxies collide, where mass hides, where gravity warps light, and where our best theories are tested not in labs, but across megaparsecs of space. We've followed that doorway deep into theory and deeper still into observation. But the truth is, we've only begun to explore what lies beyond. The ramifications of the bullet cluster extend far beyond the cluster itself. It has forced a transformation in the way we approach cosmology. This single observation, just a snapshot of an enormous, violent event, has echoed through every level of astrophysics. It challenges us not only to refine our models of structure formation, but also to ask how the cosmos itself was assembled in the first place. The implications feed directly into questions about the early universe, inflation, and even the fate of everything. When cosmologists construct models of the universe using cold dark matter and dark energy, the so-called lambda CDM model, they rely on datasets like that of the bullet cluster to calibrate and test the predictions. The lambda CDM model is extraordinarily successful, reproducing everything from the large-scale distribution of galaxies to the anisotropies in the cosmic microwave background. But it is also, in many ways, a patchwork. It includes dark matter and dark energy as necessary components, not yet understood but required to explain the data. This means that every piece of empirical evidence that supports the existence of dark matter, especially in a direct and unambiguous way like in the bullet cluster, is not just helpful, but foundational. What does this tell us about the universe? That it is not built solely from what we see. That visibility is a poor guide to significance. In fact, the bullet cluster demonstrates that what we can see is often the least relevant aspect of cosmic structure. The glowing gas is impressive, but it's not the dominant mass. The shimmering galaxies are gorgeous, but they are passengers, not pilots. The gravitational field, the real architect, is sculpted by something else. Dark matter, therefore, is not a small correction. It is not a footnote. It is the majority. More than 80% of the matter in the universe is dark matter. And if the bullet cluster had not confirmed this independently, we might still be arguing that the rotation curves of galaxies were a fluke, or the cosmic microwave background could be explained by some exotic inflationary trick. But the bullet cluster forces the issue. It says, here are two blobs of invisible mass, separated from their gas, shaping space in ways we can measure. What will you do with this? And what scientists have done is launch a full-scale campaign to understand dark matter. Particle physicists search for dark matter candidates in accelerators like the Large Hadron Collider, smashing protons together at near light speed in hopes of creating or revealing something invisible. Meanwhile, astrophysicists build direct detection experiments in underground labs shielded from cosmic rays, detectors so sensitive they can sense the passage of a single dark matter particle, should one interact. Others look to the skies, scanning for gamma-ray excesses or unexplained neutrino fluxes that could point to dark matter annihilation. None of these searches are independent. They are all informed by the bullet cluster and systems like it. Because they provide the baseline, dark matter exists, behaves gravitationally, and does not interact electromagnetically in any meaningful way. Any particle proposed to be dark matter must respect those constraints. It must pass the test of the bullet cluster. So, what kind of particle could this be? The most popular candidates fall under the category of WIMPs, weakly interacting massive particles. These are particles that do not interact via the strong or electromagnetic forces, but do have mass and therefore feel gravity. They were attractive because they could be naturally produced in the early universe in the right abundance. But despite decades of searching, no WIMP has yet been detected. This has pushed scientists to consider alternative models. One such model involves axions, ultralight particles proposed originally to solve the strong CP problem in quantum chromodynamics. Axions are very different from WIMPs. They are orders of magnitude lighter, and their behavior is more wave-like than particle-like on galactic scales. If axions are dark matter, they would form interference patterns in galaxy cores, potentially explaining certain rotation curves that WIMPs struggle with. But again, axions remain hypothetical. They too must pass the bullet cluster test. If they interact too strongly, they would not pass cleanly through the collision. Then there are sterile neutrinos, heavier cousins of the known neutrinos that do not interact via the weak force. Sterile neutrinos are appealing because they could decay into lighter particles, producing X-rays we might detect. In fact, there has been some tantalizing evidence of unexplained X-ray lines in galaxy clusters, though nothing confirmed. If sterile neutrinos are the dark matter, then the bullet cluster constrains their interaction cross-section and decay rate. Still other models posit dark sectors, mirror versions of the standard model, complete with their own forces and particles, but weakly coupled to ours. These models are complex but potentially rich, offering new ways to think about structure formation and early universe physics. But again, the bullet cluster remains the crucible. Any model, no matter how elegant, must explain why the dark matter passed through undisturbed, while the gas did not. This leads to an important point. The bullet cluster is not a theory. It is data. It is observation. It does not care what model you prefer. It shows you the universe as it is, not as you wish it to be. That is what makes it so powerful. And so dangerous to bad theories. But what about criticisms? Are there any holes in the bullet cluster narrative? Some skeptics have argued that the lensing maps could be misleading, or that the system's merger history is too complex to interpret cleanly. Others have proposed exotic physics that could mimic the observed separation. But these arguments have largely failed to gain traction. The robustness of the lensing data, the consistency of the simulations, and the inability of alternative theories to explain the offset have solidified the bullet cluster's position as a cornerstone of modern cosmology. Moreover, it is not alone. Other systems, like MAX J0025.4-1222 and Able 520, have shown similar properties, merging clusters with separations between dark matter and baryonic matter. Each new discovery strengthens the case. Each new observation adds a brick to the wall. And yet, the bullet cluster remains iconic. Partly because of the clarity of its separation. Partly because of the timing. We saw it at just the right moment in its merger to capture the physics cleanly. And partly because it came at a time when the debate over dark matter versus modified gravity was particularly intense. The bullet cluster didn't end that debate, but it changed its trajectory forever. It made it clear that any viable alternative to dark matter must explain not just one phenomenon, but all of them. Galaxy rotation curves, cosmic microwave background anisotropies, large-scale structure, gravitational lensing, and the bullet cluster. It's a high bar. But science is about high bars. It's about asking the hardest questions and accepting the answers, even when they're inconvenient. The bullet cluster has done more than confirm a theory. It has reshaped an entire discipline. It is a beacon, a benchmark, a gravitational scar across the cosmos that whispers a dark truth. Most of the universe is invisible, and yet it shapes everything we see. The bullet cluster's whisper grows louder as we dig deeper into its implications, not just for astrophysics, but for our very notion of reality. In a sense, it acts like a magnifying lens pointed at the very fabric of existence, urging us to look again at what we think we know. It's not just a story about colliding galaxies or gravitational lensing. It's a confrontation with the limits of human perception. The very fact that we can detect the presence of something we cannot see, cannot touch, and cannot directly interact with, rewrites the rules of how we define knowledge. This is the kind of realization that compels not only scientists but also philosophers to re-examine the foundations of understanding. Let's zoom back out to the broader picture. The bullet cluster event isn't a one-off phenomenon that stands in isolation. It exists within a universe governed by an elegant yet incomprehensibly vast set of physical laws. And among those laws, gravity seems to behave normally, but only when we account for something invisible doing most of the work. The gas, visible, hot, violent, was left behind, slowed by its electromagnetic interactions. But the gravitational lensing shows the mass continuing forward. This difference between where the light comes from and where the mass is has become the signature of dark matter's presence. The cluster also challenges the ways we simulate the universe. Cosmological simulations like the Millennium Simulation or Illustrious TNG include billions of particles and need to factor in both baryonic and dark matter. When we input real data like that from the bullet cluster into these simulations, we gain insight not only into the current structure of the universe but also its past and its future. These simulations recreate the universe's large-scale structure, those colossal cosmic webs where galaxies form along filaments and gather in nodes. And they only make sense if dark matter is included. But the bullet cluster gives us more than a simulation input. It gives us a benchmark. It allows us to tune our simulations more precisely. If a simulation predicts a collision like the bullet cluster and doesn't produce the observed lensing mass separation, we know the assumptions are flawed. Whether it's the particle mass, the velocity of the colliding clusters, or the model of dark matter interaction, something must be corrected. The bullet cluster doesn't just teach, it demands adaptation. And yet, while the bullet cluster confirms dark matter's gravitational influence, it also deepens the mystery. For what, truly, is this invisible substance? Here's where the philosophical edge of the question emerges. Dark matter may account for 85% of all matter in the universe, but we've never seen a single particle. That's staggering. In no other field of science would a dominant constituent of reality remain undetected in such a fundamental way. Imagine knowing a city was filled with people you couldn't see or hear or touch, but only inferred from footprints and shifting shadows. That's the world we're navigating with dark matter. This invites us to reframe our expectations of discovery. For much of scientific history, discovery meant observing something with our senses, telescopes, microscopes, X-rays, particle tracks. But dark matter lives in the realm of inference. We don't find it by looking, but by noticing the absence of motion where it should be, or the presence of gravity where there is no visible mass. The bullet cluster, in this regard, is our best indirect glance into the invisible. It is a cosmic fingerprint, a shadow cast by something intangible. And as science evolves, it will likely be remembered not just for what it proved, but for what it dared us to pursue. It's also worth noting that we live in an era of precision cosmology, and the bullet cluster helps sharpen that precision. We now know the universe is about 13.8 billion years old. We know its composition, about 5% ordinary matter, 27% dark matter, and 68% dark energy. And yet, we have only directly studied the smallest fraction of it. The bullet cluster sharpens the contrast between the known and the unknown. It's not merely a mystery, it's a spotlight on the mystery. This naturally brings us to dark energy. If dark matter explains the way galaxies stick together, and the lensing seen in clusters like the bullet cluster, then dark energy explains why the universe is expanding faster and faster over time. But here's the curious thing. Both of these phenomena, dark matter and dark energy, are invisible. They're both inferred. And yet, they govern everything. In a very real sense, the observable universe is like the foam on top of an unseen ocean. The bullet cluster is a splash in that ocean that momentarily reveals the hidden currents below. It also serves as a kind of astronomical Rosetta Stone. Just as the Rosetta Stone allowed scholars to decode Egyptian hieroglyphs by comparing multiple scripts, the bullet cluster helps us decode the universe by showing gravitational, optical, and X-ray data in one unified event. Each layer tells a different part of the story. The optical light from stars tells us where the galaxies are. The X-rays from hot gas tell us where the collisions occurred. The gravitational lensing maps show us where the mass is. And when we compare these, the discrepancy between visible matter and gravitational mass screams for an explanation. That explanation is dark matter. And if you were still hoping for a loophole, an escape from the invisible matter idea, consider this. Even alternative models like modified gravity struggle to explain what's seen in the bullet cluster. These models can sometimes account for galaxy rotation curves without dark matter, but they falter when it comes to gravitational lensing in a system like this. In the bullet cluster, gravity is displaced from the luminous matter. Any theory that tweaks gravity itself would have to somehow replicate this offset without invoking new particles. So far, none have succeeded convincingly. In this way, the bullet cluster becomes a theory killer. It's not just supportive of dark matter, it actively challenges and filters out weaker ideas. Theories that cannot withstand its evidence are discarded. That's the power of data. The cluster also acts as a kind of cosmic laboratory. Unlike Earth-based experiments, we can't control initial conditions, but we can observe the outcome of extreme events. And galaxy cluster collisions are among the most energetic and revealing phenomena in the universe. The bullet cluster shows us what happens when massive amounts of matter, both visible and dark, crash at thousands of kilometers per second. It's a test case for extreme physics. And it's one of the few natural settings where we can watch dark matter and baryonic matter respond to the same gravitational forces in entirely different ways. And then there's the future. As we develop more sensitive instruments, like the James Webb Space Telescope, the Vera-C, Rubin Observatory, and upgraded gravitational lensing surveys, we will see more bullet cluster-like systems. Each one will add to the tapestry. Each will refine our understanding. And eventually, perhaps, one of them will reveal the crack that finally lets us detect dark matter directly. Until then, we keep watching. We keep measuring. We keep comparing mass maps and light maps and gas maps, hunting for the next gravitational anomaly that says, "Here lies something unseen." The bullet cluster isn't just a key piece of evidence. It's a glimpse into a shadow world that silently governs the cosmos. It's a testament to what we can learn not by what we see, but by what pulls on everything else. And so, we find ourselves circling a central enigma, the existence of an invisible architecture that scaffolds the cosmos. The bullet cluster does more than highlight this architecture. It reveals it in stark relief, almost like an X-ray of the universe's skeleton. And the bones we see don't match the flesh. The light-emitting stars and galaxies form one image, but the gravitational lensing forms another, shifted image, a ghost image. It's that discrepancy, that spatial misalignment, that offers one of the clearest and most incontrovertible cases for dark matter. But what is dark matter really? Here, the scientific discussion forks into dozens of paths, each one leading to a different model or hypothesis. Physicists have proposed a zoo of particles that could make up dark matter: WIMPs, weakly interacting massive particles; axions, sterile neutrinos; gravitinos, supersymmetric partners; even primordial black holes. Each comes with its own theoretical baggage. Some arise naturally in extensions of the standard model of particle physics. Others demand entirely new frameworks. Let's start with WIMPs, the long-standing favorite. These particles are massive, meaning they have substantial gravitational influence, but they interact only weakly with normal matter, hence their name. The idea behind WIMPs is appealing because it ties into supersymmetry, a theoretical framework that posits every standard model particle has a heavier superpartner. One of these superpartners, such as the neutralino, could be a stable, neutral particle that fits the bill for dark matter. What's remarkable is that WIMPs, if they exist, would naturally produce the right amount of dark matter to explain the universe's current structure. This is often referred to as the WIMP miracle. And yet, despite decades of effort using underground detectors, particle colliders like the LHC, and astrophysical observations, no definitive detection has occurred. The bullet cluster helps constrain WIMP models because it limits how much interaction dark matter can have with itself. If dark matter scattered off itself the way normal matter does, we wouldn't see such a clean separation between gas and gravitational mass in the cluster. Then we have axions. These are incredibly light, hypothetical particles originally proposed to resolve a different problem, the strong CP problem in quantum chromodynamics. But it turns out axions could clump together under gravity in a way that mimics dark matter. They behave more like a wave than a particle on large scales, leading to what's called fuzzy dark matter. The bullet cluster structure again provides a test. The gravitational lensing must match the mass distribution predicted by such models. While axions haven't been ruled out, they must conform to the cluster's observed properties. There's also the possibility that dark matter could consist of massive compact halo objects, machos, like black holes or neutron stars. These would be normal objects that just don't emit much light. But the bullet cluster weakens this argument. If the dark matter were made up of such objects, we'd expect to detect more gravitational microlensing events or see evidence of these bodies scattering and interacting, yet we don't. The clean pass-through of dark matter during the cluster collision implies it isn't made of compact, colliding bodies. This leads us to another theory, self-interacting dark matter, SIDM. Unlike WIMPs, which interact only gravitationally and weakly with other forces, SIDM particles interact with each other more strongly. This could help solve some problems with dark matter distribution in galaxies like the core cusp problem or the too big to fail problem. But again, the bullet cluster sets limits. The collision shows that dark matter passed through largely unaffected, so if there is self-interaction, it must be very weak. All of this illustrates a profound point. The bullet cluster is not just a data point. It is a filtering mechanism, a kind of cosmic sieve that strains out weak theories and preserves only those consistent with its observable structure. This is science at its most powerful, nature setting the rules, and our models rising or falling based on whether they obey. And yet, we can't help but return to a more philosophical realm. The bullet cluster forces us to confront a new kind of ignorance. We used to think the universe was made up entirely of what we could see: stars, planets, dust, gas. The observable. The tactile. Now, we know this visible matter is just the tip of the iceberg. We live in a universe that is fundamentally alien to our senses. The bullet cluster isn't just showing us the invisible, it's showing us how little we ever saw to begin with. This realization changes everything. It reshapes our models of galaxy formation. It alters how we calculate the mass of clusters. It informs our estimates of the universe's total energy density. And it forces us to reckon with the limitations of empirical science. Because if something as massive and influential as dark matter can escape detection for so long, what else might lie hidden in the cosmic shadows? There's an eerie beauty to that question. It's a reminder that the universe is not ours to control or fully understand. It is vast, wild, and only partially illuminated. We are like cave dwellers watching shadows dance on a wall, interpreting them as best we can. And the bullet cluster is a shadow so distinct, so undeniable, that it disrupts our illusions. But disruption is the birthplace of progress. Every time we encounter an anomaly, a measurement that doesn't fit, a collision that defies expectations, we are invited to look deeper. The bullet cluster's quiet, gravitational whisper is a siren call to all of science. You haven't seen it all. You haven't understood it yet. And so the journey continues. Not in bursts of light, but in the curved paths of photons around mass we cannot see. Not in violent explosions, but in the subtle separation of gas and gravity. The bullet cluster is a cosmic riddle, yes, but it's also a key, perhaps even the first key, to unlocking a universe we've only just begun to decipher. As we continue to explore the implications of the bullet cluster, we start to see how deeply it resonates with some of the most profound mysteries of the cosmos. This cluster of galaxies isn't just an anomaly, it is a lens, a means by which we can peer into the very fabric of the universe itself. Through its collision, we begin to understand not just the nature of dark matter, but the deeper question of how we even begin to measure the unseen, how to validate theories that stretch the limits of human comprehension. At its core, the bullet cluster represents the dynamic interplay between observation, theory, and reality. The collision of two galaxy clusters creates an environment where everything we thought we knew about matter, visible and invisible alike, is tested. The images we see in our telescopes are not mere pictures of distant objects but are frozen moments in time, snapshots of the universe's most violent and energetic phenomena. They provide us with a glimpse into the universe's underlying structure, challenging our assumptions and pushing the boundaries of our understanding. But why does the bullet cluster matter so much? What is it about this one system that makes it such a critical piece in the puzzle of dark matter? The answer lies in the peculiar nature of the event that created the cluster. Unlike most galaxy clusters, where the dark matter and normal matter are mixed together, the bullet cluster showcases an extraordinary separation between these two components. In the aftermath of the collision, the hot gas that made up the majority of the mass of the clusters was left behind in a kind of shockwave, while the dark matter passed through the collision largely unaffected, leaving behind a distinct gravitational signature. This separation of dark matter from normal matter is a pivotal moment in the history of cosmology. It provides the first direct evidence that dark matter exists and behaves differently from ordinary matter. While ordinary matter, which interacts electromagnetically, can be slowed down and heated during collisions, dark matter remains largely undisturbed, only interacting through gravity. This insight is revolutionary, not just because it confirms the existence of dark matter, but because it opens up a new realm of investigation into the fundamental nature of the universe. One of the most exciting aspects of the bullet cluster is how it offers a potential test bed for dark matter models. As we mentioned earlier, there are numerous theories about what dark matter could be, and each theory has its own predictions about how dark matter should behave in different environments. The bullet cluster, with its unique characteristics, allows scientists to test these models and narrow down which ones are most likely to be correct. Whether it's the search for WIMPs, axions, or some other exotic particle, the cluster's gravitational lensing provides a way to see how dark matter might behave under extreme conditions. But there's more to the bullet cluster than just dark matter. The very collision of these two galaxy clusters offers a laboratory for studying the behavior of large-scale structures in the universe. Galaxy clusters are the largest gravitationally bound objects in the universe, and their interactions are some of the most energetic events known to science. When two such clusters collide, the results are dramatic. The temperature of the hot gas in the clusters can reach millions of degrees, and the shockwaves generated by the collision can send ripples through space-time itself. These events provide an opportunity to study the physics of shocks, the behavior of plasma at extreme temperatures, and even the potential for new forms of matter and energy to emerge. In many ways, the bullet cluster serves as a reminder that the universe is far stranger and more complex than we can imagine. It forces us to question the assumptions we've made about the way the cosmos works, and it challenges us to refine our models and theories. If dark matter behaves in such an unexpected way, if it doesn't interact with light or normal matter the way we thought it would, what other surprises might await us in the unexplored realms of the universe? What are we missing, lurking in the shadows, waiting to be discovered? The bullet cluster also shines a light on the larger question of how we study the universe. Historically, astronomy and cosmology have relied on light as the primary means of observation. For centuries, we've looked up at the stars, studying their light to understand their composition, distance, and behavior. But the bullet cluster reveals that there is far more to the universe than meets the eye. Dark matter, the invisible framework that holds galaxies and galaxy clusters together, cannot be observed directly with traditional telescopes. Instead, we must rely on indirect methods, gravitational lensing, for example, to infer its presence and properties. This is a crucial lesson in the limitations of our observational tools. We are no longer limited to simply looking at the light that reaches us from distant stars. We must now be willing to look beyond, to explore the unseen forces that govern the cosmos. This shift in perspective is perhaps one of the most profound takeaways from the bullet cluster. It challenges us to expand our definition of observation, to recognize that the universe is not just what we can see with our eyes or our telescopes, but also what we can infer through indirect means. In the years since the discovery of the bullet cluster, scientists have made significant strides in understanding the properties of dark matter and its role in shaping the structure of the universe. The findings from the cluster have informed the development of new theories and models of cosmology, helping to refine our understanding of galaxy formation, large-scale structure, and the evolution of the cosmos. Yet, despite these advances, many questions remain. Dark matter still eludes direct detection, and the precise nature of this mysterious substance is still a subject of intense debate. What are we missing? What does the bullet cluster still have to teach us? As we continue to study the bullet cluster, we are reminded of the vastness of the unknown. Each discovery leads to new questions, and each answer brings with it new mysteries to unravel. The bullet cluster is not just a snapshot of an event in the distant past. It is a symbol of the ongoing quest for knowledge. It is a reminder that, despite our best efforts, there is always more to learn, always more to discover. The bullet cluster may be just one of many galaxy cluster collisions that have occurred throughout the universe, but it is the first to provide such clear evidence of dark matter's existence and behavior. In this way, it serves as a beacon for future generations of scientists, guiding them as they continue to explore the mysteries of the cosmos. And as we peer deeper into the universe, one thing becomes clear: the bullet cluster is just the beginning. The answers it has provided are merely the first steps on a much longer journey, a journey into the heart of the unknown, where the universe's deepest secrets lie waiting to be uncovered. As we delve deeper into the mysteries that the bullet cluster unveils, we must also examine its implications for our understanding of the larger universe. The collision that created this extraordinary galaxy cluster is not just a curiosity. It is a window into the most fundamental forces and components that shape the cosmos. In this exploration, we confront not only the nature of dark matter but also some of the most profound questions in physics and cosmology. The bullet cluster's collision produced a fascinating, complex system of shocks, heat, and matter. Observing the gas that is left behind in the aftermath of such an event offers a rare opportunity to study the interaction of matter at the largest possible scales. The temperature of this hot gas in the bullet cluster reaches millions of degrees, far hotter than anything we encounter on Earth. This is far beyond the temperatures that could be achieved in any laboratory, making it impossible to replicate this environment in a controlled setting. In essence, the bullet cluster acts as a natural experiment, one that allows us to study extreme physics on a scale that is simply unattainable by human hands. What makes the bullet cluster particularly valuable is the fact that it represents an incredibly violent and energetic event. As the two clusters collide, vast amounts of energy are released. Gas, which is the bulk of the visible matter in these clusters, is heated to extreme temperatures, producing X-ray emissions. However, this gas is not the same as the dark matter that exists in the clusters. Dark matter is invisible to the electromagnetic spectrum, meaning it does not emit, absorb, or reflect light. Yet it still interacts gravitationally, meaning its presence can be inferred by observing the effects of its gravity on the visible matter around it. This unique aspect of dark matter makes it difficult to study, but also incredibly intriguing. When the bullet cluster's galaxies collided, the dark matter didn't experience the same friction as the gas did. This is key to understanding how dark matter behaves. It does not interact through electromagnetic forces, which is why it can pass through the gas without losing energy. The separation between the dark matter and the gas in the bullet cluster was only revealed through gravitational lensing, the bending of light around massive objects, which distorts the image of more distant galaxies. This phenomenon allowed scientists to trace the path of dark matter in a way that would have otherwise been impossible. It is this phenomenon of gravitational lensing that serves as one of the most striking pieces of evidence for the existence of dark matter. As light travels through space, it is bent by the gravitational influence of massive objects like galaxy clusters. The bullet cluster provided a clear, unmistakable lensing effect, allowing scientists to observe the structure and distribution of dark matter in the system. What was once purely theoretical now had tangible, observable evidence, providing an unprecedented opportunity to study this invisible matter in ways that were once thought impossible. However, the discovery of dark matter through the bullet cluster raised even more questions. If dark matter is indeed a critical component of the universe, holding galaxies and galaxy clusters together, why is it so elusive? Why is it invisible to the most advanced instruments we have at our disposal? The absence of direct interaction with light leads to the conclusion that dark matter interacts only through gravity, making it very difficult to detect. Yet, its gravitational influence is undeniable, as evidenced by its effect on the motions of galaxies and the structure of galaxy clusters. The fact that we have observed dark matter in action, its ability to pass through ordinary matter and interact only gravitationally, was groundbreaking. However, it also set the stage for an even deeper mystery: what is dark matter made of? For years, scientists have been working to determine the exact nature of dark matter, and the bullet cluster has only intensified this search. A variety of hypotheses have been proposed, but none have yet provided a definitive answer. Some scientists believe that dark matter consists of weakly interacting massive particles, WIMPs, while others speculate that it could be composed of axions, sterile neutrinos, or some other exotic particle. The discovery of the bullet cluster gave scientists a glimpse into how these particles might behave under extreme conditions, but it has also raised many more questions that need to be answered. At the heart of these questions is the challenge of detecting dark matter directly. While we can observe its gravitational effects, we have yet to identify the particles that make it up. This has led to the development of cutting-edge technologies and experiments aimed at detecting dark matter particles. From underground laboratories designed to detect WIMPs to telescopes seeking to observe the cosmic microwave background, scientists are tirelessly searching for direct evidence of dark matter's properties. Yet, despite these efforts, the mystery remains unsolved. Each step forward leads to new questions, and the search for dark matter continues to be one of the most exciting and challenging areas of scientific research. As we examine the bullet cluster in greater detail, we also recognize its significance in our broader understanding of the universe's evolution. The collision of galaxy clusters is an event of immense scale and energy, and the study of such collisions provides valuable insights into the processes that shape the cosmos. These galaxy clusters, which are the largest gravitationally bound structures in the universe, provide us with a unique window into the nature of the universe's large-scale structure. The interactions between the galaxies, gas, and dark matter in these clusters are fundamental to understanding how galaxies form, evolve, and interact with one another. The study of galaxy clusters like the bullet cluster also sheds light on the large-scale structure of the universe. The distribution of galaxies across vast cosmic distances forms a complex web-like pattern, known as the cosmic web. This structure is shaped by the forces of gravity and dark matter, and the bullet cluster's collision provides valuable insights into how these forces work together to form the large-scale architecture of the universe. As scientists continue to study galaxy clusters and their interactions, we can begin to piece together a more complete picture of the universe's evolution. In addition to providing insight into dark matter, the bullet cluster also plays a role in the study of cosmic evolution. The interaction between galaxy clusters is not just a local phenomenon. It is a part of the larger cosmic narrative of how the universe has changed over time. Galaxy clusters are believed to have formed early in the universe's history, and their evolution has been shaped by processes such as mergers, accretion, and the effects of dark matter. By studying the bullet cluster and other similar systems, scientists can trace the history of the universe's formation and understand the mechanisms that drive the growth and evolution of large-scale structures. The bullet cluster also helps to refine our understanding of the rate at which the universe is expanding. Through the study of galaxy clusters, astronomers can measure the cosmic distance scale and gain a better understanding of the overall expansion of the universe. This is essential for answering some of the most fundamental questions in cosmology, such as how old the universe is and what its ultimate fate will be. The bullet cluster, with its wealth of observational data, is one of the key pieces of the puzzle in this quest for knowledge. Ultimately, the bullet cluster represents a perfect example of how the universe continually challenges us to rethink our assumptions and expand our understanding. The more we study it, the more we uncover about the fundamental forces that govern the cosmos. It is a reminder that, despite how much we know, there is still so much left to discover. As scientists continue to observe, analyze, and interpret the data from the bullet cluster and other galaxy clusters, we will undoubtedly uncover even more surprising and profound insights about the universe and our place within it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.